You're listening to the Common Descent Podcast.
Hello, Will.
Hello, David.
Hello, listeners, and welcome to Common Descent Podcast. This is episode 233, the last episode of 2025. We're rounding out the year with an episode about flies and mosquitoes. That's right, this episode is about Diptera, the group of insects called Diptera, which is flies, mosquitoes, midges, all those little buzzy guys. We will be joined for this discussion by a friend of ours, Brandon Strauss, who is a forensic entomologist, who, after the announcements in the news and all that, will join us to tell us about the diversity of this group, the defining features of this group, and what we know about the evolutionary history of these famous bugs.
I just realized that I should have put just every now and then a little buzzing audio in the background of the discussion, just hear it, just to really put it on theme.
I disagree. I would hate that. But get like a clip of the noise of a mosquito right by your ear, and just every now and then.
Exactly. Yeah, that's what I'm saying. Like, so for everyone with earbuds, you just have that immersive experience. Luckily for you all, I didn't do that, but I could have. So keep that in mind.
Give thanks to Will. This episode, we're very excited. This is a topic we're both very excited about. We're excited to have Brandon join us. And this topic was requested, as all of our episodes are. This particular subject was requested by Theodora, Lydia, Lorena, Serpentine, IOC Electus, Jose, Ava, Joe, Lewis, Josiah, Gemfire, Noah, and Michael. Thank you all so much for your requests.
A whole swarm of requests.
A whole swarm. Hey, speaking of whole swarms, there's a whole swarm of supporters over on our Patreon who help to support the podcast. Like a great swarm. It's the opposite of what you normally think when you see a swarm of things.
It's a swarm.
The swarm, parentheses, happy. This particular swarm provides us with emotional support, engagement, and of course, financial support that helps to fund the entire podcast and everything that we are able to do. Patrons get all sorts of goodies, bonus content, live streams with us, merch, things like that, including at certain levels, getting your name shouted out here on the podcast. This episode, to round out the year, we would like to welcome our newest patrons, Kayla and David.
Thank you, and welcome.
Welcome. Speaking of our listeners providing us with support, we got some mail recently from Elizabeth.
Yeah, Elizabeth sent us a Christmas package with some croc and snake ornaments and art and cards. I also got a miniature version of the Crocodile Dentist game from back when we were kids.
Yeah.
And it works, and it's great. And then a little string doll croc keychain, which is also very cute, that's hanging with my croc shelf.
Amazing. Thank you so much, Elizabeth, for these lovely gifts.
Yeah.
This episode is coming out in December. As I've said multiple times now, it will be the last episode of the year, but it will not be the last thing of the year because our end of the year Q&A is going to come out right at the end of the year. Also, those of you who are fans of Leave It to Us, keep your eyes and ears out for a special little bit of bonus something or other, also around the end of the year.
Yes.
And then we're going to take a break, the two of us. You outside people won't notice that we've taken a break because the podcast will continue full steam ahead. Someday maybe we'll give ourselves a break for the holidays and skip an episode or something. It might not be. I hate the idea of doing it because it would mean breaking the pattern that we've had going for 9 years. But for our own mental health, someday we might end up deciding to do that.
Yeah. On both counts, on both topics.
Yes. But hey, 9 years after this little New Year bit, we will be celebrating the 9-year anniversary of Common Descent at the end of January. We'll have a live stream. We'll make announcements. So join us for that.
Does that make our podcast like a third grader or something? I think
We're in
About
third grade.
That's pretty good. We're
Our
like,
podcast is learning its multiplication tables.
yeah, that's pretty cool. I don't teach third grade, so I can't give detailed analogies. See you in 3 years, podcast.
My third grade teacher's name was Mrs. Skeery, and she was my favorite teacher at elementary school.
Oh, nice. I think that was Miss Miller for me, who was very sweet, but then she got pregnant, so she was gone most of the year.
Darn kids.
Mhm.
Listeners, let us know who your third grade teacher was. Anyway, with the announcements out of the way, let's move on to the news. Before we get into our main topic, as always, let's check in with some recent studies from the worlds of paleontology and evolution, things to help us keep us all up to date. Will, these are the last news of 2025, so I hope you brought some good ones.
Crocs!
All right, fine.
Right in the wire. I have to make sure. Last croc of the year. This is news about a new species of long snouted croc from Egypt that is helping to refine our understanding of the evolution of this specific group of crocodiliforms. This is research by Sarah Saber et al. In Zoological Journal of the Linnaean Society, and the article is a press release in Science Daily. This croc is from a group of crocodiliforms called the Dirosauridae. So the Dirosaurids were a group of late Cretaceous to Paleogene crocs. They looked quite similar. They were very croc shaped to our modern crocs, but they were living in a different way, on average. They were notably different in a couple of regards. Mostly they had longer, thinner snouts, so kind of gharial, but not quite that extreme on all of them. And instead of being mostly river species, they were mostly coastal species.
Okay.
And so, we have saltwater crocs today, and we have ones that are living near coast, but this was much more common for this group. So a much more salt adapted and longer, narrower snouts with lots of tiny, sharp teeth. So likely good at catching aquatic prey, but probably some of them got quite big. So probably still taking quite large prey animals. The early evolution of this group is not well understood because there is a fossil gap from about 83 to 72 million years ago. So we're missing the data there, which is part of the reason this fossil is exciting because it falls right in that gap. This is Wadasuchus kasabi and is a early member of the group from Egypt, dating to about 80 million years ago. It's based on a number of partial skulls, 2 partial skulls, 3 partial mandibles. Altogether, I think it's about 4 individuals they identified. So not like we don't have the entire animal, we don't have a nice accurate picture of for sure what it looked like, but enough to get some insight. And we do have growth stages. They are different sized individuals. So we also get a little bit idea of how this animal developed.
Neat.
Based off of the proportions of the skull and what we would predict for the rest of the body, probably like a 3.5 to 4 meter croc. So decent size.
Yeah, similar to the biggest crocs today.
Exactly. So we're, ranging up towards Salties and Niles. Using high resolution CT scans and 3D surface models, they were able to get a really nice look at the anatomy of the skull and noted that this species, differs from other members in a couple of key ways, which is part of why it got a new species, but also from an evolutionary standpoint, informative ways. It does have aspects that suggest it had a long, thin snout. So it looks like it already had developed this longer, thinner snout. It does have some key differences of having 4 teeth at the front instead of the primitive 5 for earlier members.
Okay.
Nostrils positioned at the top of the snout for surface breathing. There's also a deep notch at the tip of the snout where the jaws met. So it does seem like it is showing a transition from earlier members to later members with this development of the dirosaurid bite. Phylogenetic analysis does support that this is a early member of the group. Currently, based off this research, the earliest diverging dirosaurid that we know of. So branched off earlier than any other specimen we know of.
Yeah, so signs of the early stages in the evolution of this lineage.
Absolutely. And they also noted that it supports a transition from dirosauroids to dirosaurids. I don't know what that implies, but it implies it.
Well, again, the early development of the lineage,
Exactly.
right? The
Yes.
transition from things that weren't quite dinosaurs to things that are true, proper dinosaurs.
This also is going to shift our understanding of the origin of the group. It pushes back evidence for the African origin of Dirosauridae and suggests that their diversification began earlier than we previously thought. We typically thought that they likely diversified around like 72 to 66 million years ago. This member pushes that back to like the 80s millions of years ago. It also indicates that Africa was a spot of this diversification and that then later lineages spread out to other parts of the globe, and suggests a transatlantic dispersal from Africa to South America occurred earlier than we thought. So
Okay, cool.
it's shifting a bunch of the timing of event, nothing that we were like, oh, we didn't know this happened, but when it happened is shifted by this new species.
Yeah, so much of our discussions about life in the past and ecosystems in the past is exploring the diversity of it, right? This ecosystem was home to this and this and this group, or this lineage, the ancient crocodiliforms included these major groups in these major places. And it can be easy to overlook the important question of how did all those groups end up the way they were and where they were and in what ecosystems they were in. And these kinds of studies are there to answer those questions, which can be harder questions because those kinds of questions you need to find those really early members, those members that are a little bit less recognizable as members of that lineage. This is putting together the story of how the world got the way it was several million years later.
Yeah. They also know that this does lend support to the idea that Dirosaurids gained a narrow and long snout early in their evolution. They didn't say whether or not there had been hypotheses as to whether or not it was convergently acquired across the group. But I was interested in that since Longirostrine, the long, slender snouts of crocs, is so often convergent, even within groups. The fact that this indicates that it seems like this is a Longirostrine group that
Yeah.
developed that feature early is, for just my personal obsessions, very interesting.
Very cool. Well, hey, speaking of ancient aquatic reptiles, I've got news about mosasaurs.
Nice.
Specifically, mosasaurs in a place that we don't tend to associate with mosasaurs, rivers.
Ooh, oh, that's very cool.
This is research published by Melanie During et al. In BMC Zoology, and in the blog post, we will put a link to an article on Popular Science written by Andrew Paul. So, mosasaurs, as most of our listeners will probably remember from older episodes, episode 51 and plenty of other examples, were ancient ocean dwelling lizards. These were one of the big three aquatic reptiles of the Age of Reptiles, the Mesozoic era. Mosasaurs lived during the late Cretaceous and were found in ocean sediments all over the world. Generally, the ocean is where it is considered the place to find mosasaurs. Mosasaurs are considered a marine group. However, there have been a handful of cases over the years that have led paleontologists to wonder if they, and how often did they, move into freshwater. There have been a couple of instances where features of the anatomy or chemical studies, like isotope studies, have suggested maybe freshwater habitats, which raises that question. Were these swimming up rivers and stuff? This study presents a single mosasaur tooth that might help us answer this question. This single tooth was found from a site in North Dakota that is part of the Hell Creek Formation, episode 127, very famous formation. The site, this particular site, is interpreted as being on a floodplain near a stream. So sort of when a stream or river becomes very full during rainy season, it kind of overflows its banks and creates this little flat floodplain. Also in this site are crocs, dinosaurs, and a whole bunch of distinctly not ocean creatures. And this mosasaur tooth. The authors report that there's no evidence that the tooth was moved from another location or moved from another deposit, that it seems to have been buried in these same sediments as all these other creatures. It's in very good condition, right? So it doesn't have any of like the breaking or wear that you might expect if it was moved. So it seems to potentially be a mosasaur that lived and died in a river.
Cool. I was brainstorming through other explanations in my head, just as you do, and I was like, but what if someone ate a mosasaur at the beach and brought it up the river? But if it's in good condition, that suggests it wasn't something disruptive like
Yes.
that. Cool.
The anatomy of the tooth, the authors, it seems they were unable to, with just a tooth, link it to any particular species, but it seems to be similar to a group called prognathodonts, which are these durophagous mosasaurs with more crushing teeth. There is other material of this group of mosasaurs in the region, some of which got over 10 meters long. So these were orca-sized in some cases.
And eating tough stuff like a
Yeah, crushing
tough,
ammonites and things.
yeah, just a tough food specialist that big shouldn't be possible, and yet.
Researchers sampled isotopes from this individual tooth, the chemical composition of the enamel. They looked at molecules of carbonate and phosphate to compare with other individuals, other species. The carbon isotopes, they noted, are different from typical mosasaurs and more similar to what we might expect from a freshwater habitat. The oxygen isotopes are less similar to ocean animals like sharks and more similar to land animals like crocs and dinosaurs. And the strontium isotopes are also more like freshwater habits than marine habitats. All of which suggest that this tooth formed in a freshwater habitat.
Mm-hmm,
That
mm-hmm.
while this tooth grew in the mouth of a mosasaur, it was in fresh water. This particular region where this is found, right, the Hell Creek Formation is this habitat full of rivers flowing eastward toward the western interior seaway. There is some evidence at this time period, the very end of the Cretaceous, for the seaway, for changing conditions in the seaway. There's been some evidence for changing salinity levels or temperature levels. So it's possible that as that ocean passage was changing, some animals like these mosasaurs might have moved into freshwater habitats. This is apparently something we see in modern animals. There are a bunch of saltwater adapted animals that, as temperatures change or conditions change, will move into rivers and such.
Yeah.
This obviously is a very limited discovery. It is a single tooth, but that single tooth does seem to strongly suggest that at least one mosasaur spent some time living in fresh water, which does suggest that some species of mosasaur might have had that flexibility to move between saltwater and freshwater habitats.
Yeah, which absolutely makes sense because we see that in most groups of ocean life today. Like there are some like cephalopods just don't do freshwater. Octopus and squid just don't seem to do freshwater. But
Sure.
there are freshwater stingrays. There's freshwater dolphins. There's bull sharks which spend large amounts of time in freshwater. So it makes sense. Having evidence of it is cool. Having what seems like pretty solid at like we don't know all of the features and lifestyle of this mosasaur, but this tooth seems like a pretty solid bit of evidence. That's very cool. And now hopefully we can find more. We can keep digging in these areas and keep an eye out for more of these or more of the mosasaur.
The idea of running into a mosasaur in a river is very evocative.
Oh, yes.
That's very cool. Well, and it does make me think of those instances where you'll see images of dolphins or sharks swimming up a river. And in my mind, it's a tiny river and a giant mosasaur, which probably wasn't actually the case. It was probably like a moderately sized mosasaur and a large river.
Yes.
But the idea of a river monster swimming up, which also is a silly thing to think because there were tons of crocs around. There were already river monsters, but this is just a different river monster, and that's really cool.
I think the reason those things feel so unique and fantastical when you see them is that something that lives in the ocean, you expect it to be shaped like an orca or like a mosasaur or like a plesiosaur,
Mm-hmm.
where you are not built to touch ground. You are adapted fully for floating your entire life.
Mm-hmm.
But if you're in a river, 9 times out of 10, unless you're a fish, you are adapted to take advantage of the riverbank because the river is not so big and deep that you can just float in it your whole life as a big animal and be all right, unless you're a fish. So when we see a shark or a dolphin or a mosasaur or something like that come up a river, it's just like, no, that's you are built for the ocean. What are you doing here?
Yes.
You have no fingers anymore.
Just the biggest fish in the smallest pond.
Well, speaking of ancient aquatic reptiles,
Mm.
my next news is about a sea turtle stampede.
Huh.
Yeah.
That's a combination of words that I didn't expect.
Which sounds like a clickbait title, but is actually very accurate.
That's awesome.
This is research by Paolo Sandroni et al. In Cretaceous Research, and the article is by Elizabeth Rain in Popular Mechanics. So, this is a site of preserved trackways, trace fossils that were discovered on a mountainside in Italy by free climbers. People were
Mhm.
climbing the mountain and came across these trace fossils that are footprints, which is the accurate term, but flipper prints.
Right.
These patterns in the rock, a slab of limestone, and they called it in, and further research came to look for it. They found another section of the same layer exposed in a more accessible area, it seemed, and that gave them more information that allowed them to both date the site, which dated to about 83 million years ago, so actually about the same age as the Diosaurid.
Yeah, and just a little bit older than that mosasaur.
Yep. A lot happened in the coasts during this million years. And identify that these are flipper trackways and a bunch of them. There are a whole bunch of trackways and traces of a numerous amount of individuals all moving seemingly at the same time. They were most likely made by some medium-sized aquatic animals based on the type of flipper patterns, not fish, but something with limbed flippers like a sea turtle or maybe mosasaur or plesiosaur or
Mhm.
pliosaur or something like that. None of those are preserved in this deposit, so we don't have like a animal to point at as the likeliest, but based off of the patterns and the type of environment it was, they are leaning toward probably ancient sea turtles. Now, these would be Paleostegidae sea turtles, not our modern groups of sea turtles, but an ancient lineage of marine turtle. Very similar. Part of the reason that they're leaning toward turtle over the other members is that it's a seemingly mass gathering. And if these turtles nested like our modern turtles do in these big gatherings, that would explain that. They also noted that the type of environment it is when we know modern sea turtles frequent and is a type of area that we have seen at least some species resting on the sea floor. So it fits the MO of a sea turtle. And so that's what they are leaning with
Mhm.
as their current hypothesis for the creators of these tracks. This is being called a stampede because it seems like a bunch of sea turtles were resting on the very silty, muddy bottom and suddenly all moved in, if I remember right, they said an eastward direction, but they all moved at once in the same direction together, and some of them leaving paddling trackways in the mud,
Mhm.
and that this mud would not preserve trackways well unless it was immediately buried, which it does seem to have been by sediment from an earthquake. And that what
Oh.
likely happened is a bunch of sea turtles were resting, an earthquake happened, spooked them, they all swam off, and then the sediment shifted from that earthquake, buried this layer very quickly, and preserved it.
Ah. So these turtles fled from a landslide,
Yeah, yeah,
an underwater landslide, a
exactly.
turbidite, as we call them, a turbidity flow,
Yes.
which leaves a turbidite, a layer of sediment.
And based off the sediment in the area, it does match that. That it shows evidence of seismic disturbance, is what they said. And based off of the dating of the site and our current understanding of the technoseismic history of this paleobasin, it coincides with a period of climatic change known as the early Campanian event, which has been suggested. This got thrown out by the news, has been suggested to have been triggered potentially by an asteroid impact, which
Okay.
has led people to connect that in the articles.
Sure. Asteroid hit, caused an earthquake, caused a
Yes.
landslide, spooked a bunch of turtles, which is a lot harder to link all those
Yes.
things. The earthquake, landslide, turtles makes a lot of sense.
Yeah,
That's
that
pretty
seems
that's pretty solid.
solid. That the sediment suggests that, the patterns in it suggest an earthquake happened, and that the only reason these tracks were preserved was because of this sudden landslide of earthquake material. The rest is a neat idea.
Fascinating. As usual, trace fossils are so fun because they record the
Mhm.
behaviors and movements of ancient organisms. The idea of this being sea turtles, so much of the identification of these tracks as being sea turtles seems to be based on what we know about sea turtles, which is a perfectly valid reason for that hypothesis. Sea turtles are in an unfair position in that regard because we really don't know hardly anything about other marine reptiles from that time in terms of their
Yes.
behavior or their if they were social, if they were hanging out on the bottom like that. So very fascinating to think about what animals were there other animals in that area. Even if these were sea turtles, was there a bunch of fish that were also swimming in the same way? Was this just a flock of birds coming out of the forest after
Yeah,
an earthquake or something? Was it just a whole bunch of animals moving away?
absolutely. And you make an excellent point about us not knowing the behavior of a lot of groups. The news article had a mention in it of like modern sea turtles are usually pretty solitary, and so were pliosaurs. And that's one of those where we don't have evidence of mass gatherings of
Hmm.
a lot of marine reptiles, but that doesn't mean there weren't social events or periods where that happened. So it absolutely is a case, and they didn't seem to mention anything of like, based off the shape of the trackway, it fits sea turtle best. Just some flipper limbed vertebrate, which leads us to marine reptile for the time.
Right. Most likely turtle.
Seems like turtle's probably the safest bet, but absolutely it could have been another member if plesiosaurs also grouped together during mating times or something.
Yeah. Pretty cool findings. Well, speaking of ancient aquatic reptiles, I've got one more news to do. Our last news of 2025, and it's about snakes. Specifically about the evolutionary history of giant anacondas in South America.
Cool.
This is research published in the Journal of Vertebrate Paleontology by Andre Alfonso Rojas, and we will link in the blog post to a press release from SciTech Daily from the University of Cambridge. Green anacondas, you may have heard of them, are among the largest living snakes. They do set the record for the heaviest living snakes, and they achieve some of the longest lengths of any living snakes. Green anacondas average between 4 and 5 meters long. So, 13 to 16 or so feet long. That is average for green anacondas, which is a preposterous number. The max size of anacondas can be 6 to 7 meters. They can get very, very long. But not a lot is known about when they evolved those giant sizes. This study combines information from fossils and modern species to infer the origins of anaconda gigantism.
Cool.
They examine a bunch of fossils from a number of different localities in Venezuela, which range from the middle Miocene to the late Miocene, between about 12 million and 5 million years ago. These fossils include a bunch of different snakes, so there's numerous different species, including multiple specimens of Eunectes, which is the genus that modern anacondas belong to. Based on the proportions of the vertebrae, they infer the total body length, because we don't tend to get a whole snake skeleton, we tend to get individual vertebrae, but there are pretty well established equations you can use to measure the vertebra and estimate how big the whole snake was. They find that throughout these different sites, the fossil anacondas on average were around 5 meters long, which makes them similarly large as modern anacondas. They also did a phylogenetic analysis to infer an ancestral state reconstruction. Basically, taking all of the boas and their relatives, this is the group that anacondas belong to, looking at their various features in an evolutionary tree, and coming up with the best estimate of what the early versions of these lineages would have looked like. What features were most likely present in early members of each group. This analysis estimates that the anaconda genus, Eunectes, originated around the late Eocene, and the modern species split. Today we've got green anacondas and yellow anacondas. They estimate that those two species split in the early Miocene, which it sounds like is a little bit earlier than previous studies have estimated, and that the earliest members of this lineage started probably around 2 to 3 meters long, which is a pretty typical size for big snakes. Right?
Yes.
2 to 3 meters is about as big as North American snakes get, for example. And by the beginning of the Miocene, in the early Miocene, they are estimated to have reached around 4 meters, getting into these big sizes. This is consistent with these fossil finds of middle to late Miocene anacondas being on average around 5 meters long. So this does seem to together support this idea that anacondas began reaching these giant sizes during the beginning of the Miocene epoch. Which then, of course, raises the question of why did they start reaching those giant sizes at this time? The authors point out that this time period is concurrent, same time, as the origin of what is known as the Pebas wetland system. Yep. This is a famous extensive habitat that is known from the Miocene of South America. Extensive wetlands, evidence of rivers and lakes, and just this mass, basically like a super Amazon.
Yes.
That was there throughout most of the Miocene epoch. Notably, this habitat in this time period is associated with the appearance of several different giant aquatic reptiles. These include Stupendomes, which is an ancient side-neck turtle that was gigantic, as well as multiple lineages of giant caimans.
Yep.
This is where Purosaurus is from. This is where Morasuchus is from. These were caimans, right? Alligator cousins that reached, these guys got to 30 feet long?
Oh, yeah. Like 20 to 30 feet. There were multiple species that got above 20 feet and a few that reached up to 30 feet. And yes. Purosaurus has been estimated above that for the very largest specimens, potentially.
So the Pebas wetland system seems to have encouraged the growth of giant reptiles. These other ones, including giant anacondas. The larger sizes are possibly linked to high temperatures, the availability of lots of food. Maybe also, it's been suggested there might have been lower competition because there was such a resource-filled environment, or lower predation pressures. Some combination of factors meant that this habitat at this time was the place to evolve into a giant reptile.
Which is so cool.
Notably, the Pebas wetland system comes apart in the late Miocene as there's uplift, probably of the Andes, climate cooling throughout the world. And as that system sort of breaks up to give rise to the more modern habitats there, the big reptiles disappear. The giant caimans and the giant turtles vanish, but anacondas did not vanish. They seem to have stayed that size even after this system left. The authors do look into the late Miocene and afterwards and find that there is some evidence for a size drop in the late Miocene among anacondas, But the fact that there's not a lot of fossil evidence to go on, and the fact that they're still that size today, the authors suggest that probably there wasn't a significant drop in size at any point. So anacondas seem to have reached their gigantic size around the same time as all these other groups were. But for some reason, when all the other groups lost that, when those giant species disappeared, giant anacondas stuck around. And what exactly it was that allowed them to stick around, we don't know.
Yeah.
Probably some sort of flexibility, some sort of ability to utilize a bunch of different habitats or a bunch of different food resources. Somehow anacondas survive.
Well, and it makes me wonder if they hit a sweet spot of like, because Purosaurus is on the upper end of crocodilian size, period. Like, it's the same size as Deinosuchus and Sarcosuchus and Gryptosuchus, the largest crocodilians that ever lived. Purosaurus is equivalent in size to all of those. That seems to be as big as a croc can get. And Stupendimes is also one of the largest turtles that ever lived. Anacondas are very big, and they're our biggest snake today, but there have been snakes that got bigger. I wonder if the anaconda hit on a giant size that was reasonable enough, because like there's still big crocodilians down in South America. The Orinoco crocodile and the black caiman both are some of the largest species around today.
Right. They're anaconda sized.
They're anaconda
sized. They reach
sized.
similar lengths to anacondas.
So I wonder if the anaconda hit a size that meant it didn't have to rubber band back like the other groups did to smaller sized members. If it was like, no, I hit my resident frequency, like my just ideal size, and was able to maintain it because it didn't hit the crazy upper limits that would have made it unstable.
Yeah, that there is perhaps more opportunity and possibility for survival for a 20-foot snake than there is for a 30 or 40-foot caiman.
Yes, exactly. Yeah.
Yeah.
Very cool.
Fascinating study. Also, it's always so fun to discover something like that is ancient.
Yes.
That's like, yeah, apparently South American anacondas have just been that size for 10 million years.
Yeah,
and that's just what's been around.
That's very cool. This also, for me, very much feels like one of our moments of like, if I could kit bash episodes together, go back to the alligators and caimans episode where we talk a whole bunch about this mega wetlands and add this news into that discussion.
Yes, that was episode 194. And then go back to the boas and pythons episode.
Yeah.
Which was episode 196, where we talk about anacondas and their giant relatives.
Like, just smush all those together, and you have this ideal little episode about these awesome big reptiles. Man, I love that wetlands so much. That super wetlands. Why don't we have those today? It's not
the place
fair
to be.
Ugh.
That's the news, which means it is time for us to move on to our main event. We are going to take a short musical break, and then after the break, we will be joined by our special guest, Brandon, to tell us all about some of their favorite bugs. Hello, Brandon.
Hi, David. Hi, Will.
Hi, Brandon.
Thank you so much for joining us. We, for our listeners, we talked to Brandon this year at DragonCon and settled on the perfect episode to bring you on as a guest to talk about flies and mosquitoes. We're so excited. If you would please introduce yourself for our audience.
So, my name is Brandon Strauss. I am a PhD candidate at Texas A&M. I specialize in flies. Specifically, I'm a forensic entomologist. I specialize in all those decomposers that also happen to be pollinators.
Yeah.
Yes.
We're going to talk about that later.
I can't wait. It's going to be great. Brandon can often be found among the science track people at DragonCon talking about the gross stuff.
Yeah, most of that stuff is not appropriate for this podcast.
Yeah, those are after 10 p.m.
Oh yeah, those are 10 p.m. plus panels. We go for 2 hours, sometimes 2 hours and 30 minutes, and it's a packed room, and everybody loves it. For some reason, everybody loves the weird, gross stuff.
Well, we are thrilled to have you join us. Like I said, this episode's topic is flies and mosquitoes, the order of insects called Diptera. So before we get into any details, this is a huge group, some of which is familiar to our audience. Brandon, if you could please give us just briefly who is in this group of insects.
Okay, so even before that, I have to start with the common name situation. Because
Sure.
dipterans are true flies, right? We have the word true fly in quotation. But you also have things like butterflies, dragonflies, lanternflies, right? All these things called flies, but they're not dipterans, right? Think about like dragonflies are odonata, right? Lanternflies are hemipterans, right? So we have this actual naming scheme in entomology where if there's a gap between the name, it belongs to that group, right?
Okay, interesting.
Yeah, so if you look at like a blowfly or a housefly, there's a space in the common name. But think about the word
Yeah.
butterfly. It's one word,
Yes.
right?
Yes.
This is a common thing in entomology. Now, it breaks the rules and grammar of everything else,
Sure.
but this is how we do it, right?
Yeah. If there's no space, it's a new word for this other group. But if it's a space, then this is the adjective describing this fly.
Exactly.
Like seahorse
Yeah.
Yeah.
is not a whore. That is not a type of horse.
Right? Exactly.
Cool. Oh man, I'm gonna be looking at that in bug names from now on. I'm just gonna
Oh,
go on,
yeah.
space, no space.
And you will see it in news articles all the time, and we'll see it in like books and novels, and I'm just sitting there going, there's no space. What are you talking about?
So this episode, similar to our eels episode 198, where we did have to make mention of the things that are called eels that are not actually eels. This episode is going to be a little different, where I think we're probably not going to talk very much at all about things that are called flies but are not actually flies.
When we get to the fossil record,
Okay.
we're going to talk about
All
that
right.
a little
Okay.
bit. We're
Can't
going to talk about that a little bit. All right. So, what are dipterans? These are the true flies, and we actually split these into two suborders. So you have our more basal, ancient, quote, primitive flies that are called Nematosera or Nematocera. And then you have Brachycera or Brachycera or Brichybrax, or however you want to pronounce it. The flies didn't tell us how to pronounce it. We just came up with the names.
Yep.
And the Nematosera are the ones that include like mosquitoes and crane flies and all those more ones we find in the fossil record, right?
Yeah,
They're the ones that people think about and they go, dinosaurs. And then, And then Brachycera are your more stout-bodied flies, right? You're thinking house flies, you're thinking blowflies, flesh flies, things like that. Now, this is what I use. This is what people in my department use. This is what we teach. Because it gets a little wibbly wobbly, timey wimey. Because there's another group in there called Cyclorapha that used to be its own separate suborder. And then sometimes it's an infraorder in Brachycera. And then sometimes it's actually couched within another infraorder called Muscomorpha, or sometimes it's all in the weeds and complicated.
True. So it's somewhere
It's
in there.
Somewhere. People are probably fighting about it right now at the Entomological Society meeting. Like, it is nuts.
I feel like as soon as I see the term infraorder, I go, okay, so it's complicated. You're in this overall group. That's as much as I'm going to take away from this.
Yes. I think the Linnaean taxonomic groups, kingdom, phylum, class, order, family, genus, species, are not great for accurately representing the diversity of life, but they are great for letting me know where I need to stop going into any more detail. If you're not in one of those, then this is too complicated and I don't need to worry about it.
There were a few papers I read for this podcast that were like, so the Linnaean classification system didn't work, so we just got rid of that. And I was like, oh, cool. Okay, fine.
So, speaking of that diversity, one of the things that stands out when I think about flies, because in my head, flies are flies, and there's flies, and I know that some of them have different names, but I also know deep within my bones that flies are a preposterously large and diverse group of insects. I want to say they're one of the top, alongside beetles and other really big ones. So, Brandon, what is the how many flies are there? Where do they live? What is their general sort of diversity and distribution?
So they are the big four, right? You've got Coleoptera, you've got Diptera, Hemiptera, Lepidoptera, right?
All right,
And
so beetles, flies, true bugs, and butterflies.
butterflies in there. There are about 160,000 species of Diptera, right, in the world today, right?
Whew.
Think about that. 160,000. How many vertebrates are there in the world?
Right?
Not a lot.
Not a lot.
No.
Right.
Mammals are coming in at maybe 6,000.
Yeah. So if you look at like Nematocera, right, our real basal group, one of the families in there, Tipulidae, which is our crane flies, there's about 10,000 species. And they are represented in the fossil record. They've been here for millions of years. They're going to keep being here. When we look at mosquitoes, Culicidae, there's about 3,600 species. They've been here for millions of years. And then you get into the more recent flies like Brachycerans, which involve Calophoridae, Sarcophagidae, and you're looking at 1,500, maybe 2,000 species here or there, give or take. Just a couple thousand flies in one family.
Just a couple thousand.
Yeah, nothing too crazy.
I mean, these are insects that live fast lives and reproduce a lot. So it's not surprising that they've achieved that kind of diversity.
Oh yeah. The radiation events that we're going to talk about later are absolutely fascinating. Very interesting.
So are flies ever? I assume that if someone to stop me on the street and ask me, I would say that flies live everywhere but the poles, and I assume that that's true.
They are on Antarctica.
Oh well, all right.
And they are in the Arctic Circle. They're everywhere.
Foolish me! I thought you were going to correct me and point out places that no. In addition to the poles, they also are found in XYZ. But instead, you said no. They're at the poles too.
No, they're there. They're there. Their only place they're not is like the ocean and like the deep sea. Like
sure.
Yeah. There's no like giant fly in the Marianas Trench. Just waiting.
Yet.
Yeah. No, there's flies that are at the poles. They're black flies in the Arctic. I mean, if you go and talk to anybody in northern Canada or anything in that area, black flies, these are these biting flies that come out in the summertime. They transmit diseases and all sorts of stuff. They're fun.
Well, and they have those like crazy huge like conglomerations, those giant swarms.
Mm-hmm.
And as you said, the Arctic Circle, I went, right, that's where that's happening. I always forget when I see it in documentaries because they don't like show the temperature to remind me that we're up north. But yeah, flies are intense.
Oh yeah. And then the one in Antarctica, it's Belgica Antarctica. And these guys are interesting because they're so adapted to the cold down there that actual like body heat kills them.
Wow.
Like if you were to handle it with your hand, your temperature of your skin would just kill that fly.
That is so intense because like so often we emphasize that like insects are cold blooded.
Mm-hmm.
They need the heat from their environment to function. So that's why we typically don't see them in cold places. The fact that they are so well adapted to that they have now kind of come back around to where heat is the enemy.
Yeah.
Flies are extremophiles.
Yep.
That's really interesting to me because, and at the risk of going off on a tangent, back in episode 179, thermoregulation, we talked about how insects build up heat in their wings, particularly to warm those muscles enough in order for them to be able to fly.
Yeah.
So do these flies fly?
They're mainly in the snow. They're mainly walks.
That's a preposterous. They're trudges.
They're trudges. They're snowshoes, right? Whatever you want to call them.
Snow flies is wild.
Yeah.
Snowfly, don't bother me.
Yes.
Oh.
Well, I know we could sit here for the entire episode and
Yeah.
just have Brandon shock us with what types of flies there are, but
Yes.
that's a different episode of someone else's podcast. So let's zoom out and get into some of these broader and yet also more specific details. Brandon, we're talking about Diptera, the order of flies and mosquitoes. What are the defining features of this group? What makes dipterans different
Oh.
from other bugs?
So we're start basic. Everybody knows they're insects. We start with
Mhm.
insecta. We got 3 body segments, 3 pairs of legs. That's normally where we all start. We look at the antennae first, start at the head, work our way down. In Nematosera, we actually have this long filiform and sometimes feathery antennae that goes longer than the head and the length of the thorax usually. So you think of this really spindly, like think of mosquito, think about a crane fly, think how long and thin their antennae are.
Mhm.
This is characteristic of Nematosera. Then
Okay.
you have Brachycera, where we have the body plan changes, right? We get that short, stout fly that looks like a bad bread loaf with wings.
Yeah, they look kind of like a bullet.
Yeah, like a little bit of bullet, a little bit of just a kidney bean.
Yes.
Right.
Mm-hmm.
And then they have these really shortened, highly modified antennae that come in 2 forms. One called stylate, which are like these little like V horns that come off the head.
Mm-hmm.
And then we have aerostate, where there's like a lobe on the front of the face. If you've ever looked at the face of a fly, you see that weird lobe that looks like 2 kind of like noses hanging down.
Mm-hmm.
There's a little feathery hair that comes off. That entire structure is the hair is the arista, and that entire structure is the antennae.
All right.
Oh,
Yeah.
wow.
So we've got lobed, long and feathery, and devil horns. We'll talk about why those are devil horns. We stick with the head though, as we move forward, right? The most obvious is that there's mouth parts, right? We look at the mouth parts, but sometimes there's not mouth parts.
Yep.
Right.
Sometimes flies, as adults, said, I don't need to eat.
No,
Right?
no,
I don't need to
no.
get into that. That's messy. I ate as a larva, I ate as a kid, I developed, I'm fine. And that's like crane flies. A lot of crane flies do not have mouth parts. So when someone calls them, oh, that's a mosquito killer, or it's a giant mosquito, or a mosquito hawk, I'm like, it ain't even got a mouth to go to a flower to take some nectar.
Mm-hmm.
Right?
Which really does distinguish them from mosquitoes, whose most famous feature is their mouth parts.
Exactly. Like some of them have like a little proboscis that folds out, and it's like a little like forked tongue, and it's like that's about it. There's also bot flies. A lot of bot flies do not have mouth parts as adults, right? Their entire purpose is to get their larva into a host.
Interesting.
But then as we move into things that actually have mouth parts, most dipterans have what we call haustellate mouth parts, meaning they're adapted to ingest liquid foods.
Mm-hmm.
So iconically, mosquitoes, right?
Yes.
You've got the piercing, sucking mouth part. It's most prevalent in Nematosera. There's a very ancient basal characteristic that we've seen kind of through the fossil record there. It's also pronathous, right? Which meaning it juts forward from the head.
Mm-hmm.
Versus in Brachycera, where we start to see things differentiate. So you've got sponging, you've got piercing, you've got sucking, you've got knives on the face, just knives, and the knives have a sponge underneath, and they cut you with the knives, and then they sponge up the blood.
Oh, interesting.
Yeah.
Yeah. So it's like that typical like housefly mouth part, but they're cutting you first and then just.
Yes.
Oh,
exactly.
wow.
Yeah. So if you look at certain flies, they might have like kitchen shears, or they're just like 3 blades, like in certain like tachinids that just like cut you, and that's why it hurts.
Yeah, that's
'Cause
why
you're
it's a
not-
bite.
Yeah, you're not getting a nice little needle to poke in you. And like, oh, here's something. It's small, it's tiny. It's like, nah, they shank you and then they take your blood.
Yeah.
What a low-tech way to eat blood.
Yeah. So a bite from a fly is not a bite, right? Well, because we think of some insects like ants that have mandibles that will actually close on something.
Mm-hmm.
But dipterans, it's mostly piercing and stabbing.
Yeah, it's piercing, stabbing, and slicing, right?
Okay.
They do not have mandibles in the
Mhm.
traditional sense of what you think with like an ant or a beetle, right?
Mhm.
There is no dipteran with that, right? The
Okay, interesting.
larvae have some mandibles, but the
Yes.
adults do not.
Gotcha. And this is, while we're talking about the features of flies and insects, flies also, and I'm saying this because I didn't put this in the outline, undergo complete metamorphosis.
Yes,
Episode
correct.
81, they start out as little larvae or maggots. They go through, I believe, usually, if not always, a pupa stage, and then they come out as winged adults.
Usually winged adults.
Sure,
So there's
yes.
that's we have to put an asterisk around everything here
Yeah.
because it's
Yep.
insects.
Because there's 160,000 species, and
Yes.
some of them are breaking the rules.
Oh, there's so many that break the rules. We'll talk about that later. But yeah, so like the horsefly, the deer fly, and those ones that cut you, what's interesting with them though, that bite hurts. You're gonna slap at it, right?
Yeah.
Their bodies are so robust that they've literally evolved to take that slap.
Yeah. Yeah.
They're like a horse will slap it with the tail, and the fly's like, whatever. Like,
Yeah.
it's fine. You got
No,
more?
I noticed that one time when I swatted at I think it was a horsefly, and if not something similar, and I made contact, and it felt like hitting a little aerial rock.
Yeah.
It was so tough and dense, and it just went whoa and kept flying.
Yeah.
And I went, okay, that you are in a league I am not ready to deal with.
It looked at you like Captain Marvel after Thanos punched her. It's like, you want to try it again?
It just tanked the hit, right? It's just
Yeah.
like, fine. I don't even need
Just-
heals.
So
Wow.
robust.
That's one way to do it. That's one way to be an ectoparasite.
Exactly, right? Like, do I want to sneak in here? Nah, tank the hit, baby. Let's go.
It's just sitting there drinking. Stop it! No! Stop it! No!
So, moving on from the mouth parts, we then have our eyes. And, they're insect eyes. You guys have talked about this in previous episodes. They're made of ommatidia, which I always think of like as fluorescent light tubes kind of stacked vertically
Mhm.
and then put together, and they see in a mosaic. The head shape with the eyes changes from Nematocera to Brachycera, obviously, right? If you think about a housefly head versus a mosquito head, one is a lot more rounded and bulbous. The other is kind of more like almost like a dumbbell, right?
Yeah.
With eyes on the side. Yeah. And that's part of what makes one of the physical distinctions that we see as they separate is that rounding of the head, shortening, stouting, and the enlarging of the eyes. Because some flies, the eyes will meet at the top of the head completely.
Yeah.
Yeah, like with Sonic the Hedgehog. The eyes are joined as one.
Oh God, I just remembered that. Thank you for that memory. And then we move away from the head and we talk about the thorax. Now, I'm going to put a disclaimer here because it's kind of a warning, we could get into the weeds about this, and we're not going to. But for anybody who wants to study flies, this is what I'm putting it out to you, especially you student who is listening to this thinking, I want to be an entomologist. A lot of fly identification and classification is through a thing we call ketotaxy. Ketotaxy is the study of the orientation and placement and patterning of the hairs and bristles and setae on the exoskeleton of the arthropod.
Really?
That sounds terrible.
Yes. Every single one of those hairs, those bristles, has a specific spot and placement on the body. They've all been numbered. They've all been labeled, right? They have been weighed. They have been measured. We know where they should be.
Now, that does sound wild, but on a bigger, to back it out a little bit and find a comparison, we also do that with reptiles and their scales. Right? If you look at a field guide, they'll say, here's how you identify this snake. Its color pattern is like this. The shape of the head is like this. And then the scale row, it has 5 rows and blah, blah, blah. That's usually the part where I stop paying attention. And I go, I'm not going to be able to see that. So it doesn't surprise me that we've done a similar thing with insects.
Yeah.
But the idea of counting the hairs on a fly sounds just daunting as heck.
And remember, there's 160,000 species of flies.
Yes.
Yep. Well, this is also, I think, now my new favorite way to emphasize that insect and arthropod hairs aren't hairs. they are a separate structure from mammal hair. Because like
Mhm.
if you try to do this with mammals, people would just look at you like you're insane. Of like, well, okay, but where does the hair come out? From wherever it wants.
How many hairs does this cat have?
At least 5.
Yeah, like wherever a pore can fit. I have hairs on the tip of my nose that
Yep.
have decided to start coming. That's not consistent. These are not the random structures like we see on a mammal skin. These are different and very consistent structures.
Yes, exactly that. So we've got CD, you've got setulae, which are even finer hairs, and then you've got bristles, which are just larger hairs. It's yeah. So anybody who wants to go into this, just be aware that a lot of us just look at fly hairs and cry. Like that's just a daily occurrence.
I got the picture of the image of the South Park episode where they try to do their own stop motion, and then one of them sneezed right before finishing it.
And everything is just ruined. Yeah, it's exactly that. So moving away from the nightmare that is fly hairs, though, the most notable thing that people usually catch on to with flies is how many pairs of wings they have.
Mm-hmm.
It's right there in the name.
It's right there. They only have one pair.
Yes.
Right? So, which is funny, they're called Diptera, right? 2 wings. A lot of people would think, oh, wait, but there's only one pair. Wouldn't that mean Diptera? Wouldn't that mean 2 pairs? And Latin is weird, and we won't go into that because it makes the brains hurt. But they have 2 wings, right? They only have 2 wings because the hind wings have been highly modified into a ball on a stick.
Yeah.
And this ball on a stick is called a haltere, and it is this highly modified, specialized organ that's essentially a gyroscope.
Yeah.
This is what allows the fly to be a fly. It keeps them oriented in the air. It literally allows for like instantaneous changes in movements because it's so sensitive. That's why it's so hard to swat a fly.
Yeah.
Yeah.
This is my favorite fly feature.
And that is something that, for any of our audience that don't have insect anatomy in their head, saying that they have 2 wings from a vertebrate perspective sounds like a very obvious thing to say because all flying vertebrates have 2 wings. But the default in insects and flying insects is 4 wings, 2 pairs.
Correct.
Right? If you think of your dragonflies and you think of most of your flying insects, having just the 2 is a real, what would seem like a real downgrade for this group of insects. But they've compensated by turning those other 2 not wings anymore into structures that make their flight even better.
Exactly. And a lot of insects have modifications to the wings, right? But usually it's the forewing. That's also what makes flies stand out, right? Beetles have the elytra, the forewings now a hardened shell. Hemiptera, some of them have the hemelytra, it's leathery. Grasshoppers, so many others have the tegmina, that's the forewing is shortened, it's hardened, it's leathery. Even Strepsiptera, they have halteres, but it's the forewing again.
Huh.
I was going to say, I was surprised when you said the hind wings, because I usually think of things like beetles, where the front pair of wings is what's been changed.
Exactly. So many things, the forewing is what's highly modified. In the flies, it's the hind wing. It's also what makes them stand out.
Cool.
I never made that connection. That's cool.
This is why I love flies, right?
Yeah.
So, as they are flies, though, we'll talk about the legs. And there's not a lot going on, right? They're mainly there for walking, some running, some scuttling in some flies. We have things called scuttle flies. We also have a thing called keds, which are hippoboscids. And they're the ones that got rid of their wings. And they developed, well, some of them. They developed highly modified legs to hold on and grab and stay attached to a host.
Sure. Yes. Like a tick.
Like a tick, exactly. And they look like ticks. If you go and look up photos of these guys, a lot of them look like ticks. The proboscis looks like a tick's mouth parts sticking out from the face with spines on it. They even have the head and the thorax kind of have moved into a cephalothorax, and the abdomen has widened out and flattened. And they are the ectoparasites. A lot of them are the only ectoparasites on bats.
Yeah.
Because bats do not have ticks that affect them. They have keds. And these keds have evolved to look like ticks.
Wild.
Right?
Yeah.
160,000 species.
Yep.
Yeah. There's a fly for that.
I learned of these not too long ago. And they look so sci-fi. They are so, like, It looks like a thing that would cling to the face of a bat.
Yeah, like if this got on your face, you would expect eggs and then like, from your chest.
Yeah, exactly. Yep.
I mean, but like we also have a thing called like the stilt-legged fly, right? There's a whole group of them, whole family of them, and some of them, the second pair of legs are elongate, and so they mimic the walk of like ants, and so they're like an ant mimic, and the leg helps them look like ants. It's wild.
Huh.
So yeah,
I love that even among this like the group that is flies, there's still ones that mimic ants because all must bow to ants at some point.
Everything has to bow to the throne that is ants.
Yep.
Now, that was adults. I got to talk a little bit about larvae.
Sure.
Right? That's important. So most larvae, a lot of larvae for Nematocera live in aquatic environments. Right? So there's this separation of resources, this partitioning of resources. And because they're aquatic, or if we're in Brachycera, they're in decaying organic material, or even in Nematocera, they're decaying organic material. The body plan's simple. It's very simple. It's a tube, and food goes in one end, and food goes out the other end. But sometimes air comes in one end, but it's the opposite end that the food goes in.
Yep.
Right? So Nematocera, we see the difference is that you've got this long cylindrical body, you've got a head capsule, a sclerotized head capsule, so it's hardened, it's got some mandibles, and then some fun, funky stuff there, right? Whether it's in the water, whether it's in soil, then we get into specializations. Now, picture a maggot, right? You got a maggot in your head? Cool, that's Brachycera. There you go. They might have a tail. There's no head capsule, right? They're just soft, little, meaty grain of rice, and that's it. Right? They've been described as squishy and worm-like, and there's a lot that's going to differ genus to genus, family to family, species to species, but we're not going into that. So I'm going to leave that there for the physical characterization of these guys.
So you mentioned that Nematocera, the larvae tend to be aquatic, right? That you think about where you find mosquitoes, right? Standing water, that's where those larvae are.
Yep.
And then in Brachycera, the larvae are often in soil or in decaying matter.
Yes.
And I assume that could be plant material. Very famously, it can be animal material, right? Carcasses, the flies who are hanging around carcasses laying their eggs. Are there aquatic adults in Diptera? Are there any swimmers?
No. There are ones that'll go like maybe onto the water, but you don't have anything of like in Coleoptera, like waterback swimmers, beetles. Same thing like Hemiptera. There's no notonectids.
Okay, cool. I expected the answer to be no, and I'm delighted to have been correct.
Right. In Nematocera, you also do have some larvae that are terrestrial, and they're like soil dwelling.
Yeah.
So again, you still have this kind of like niche partitioning, right? So the larvae are always using resources that are slightly different than what the adults are using.
Yeah.
Even if like adult like blowflies are going to a carcass and there's maggots there, they're only there briefly. They're not using it as a main resource.
Yeah.
Right. Well, and as I understand it, a lot of flies that are feeding on carcasses are feeding on the fluids, right? They've got those sucking mouth parts, whereas the larvae are chomping and eating at the meat, I would assume.
Yeah. So the ones that are the meat eaters in the Brachycera that are larval, they have mouth hooks. So imagine a grain of rice that then you put like 2 meat hooks at the tip of it. And so they're scraping and pulling that in.
I love the theme that is emerging in this episode of Brandon saying, imagine this, and then describing something that I do not at all want to imagine.
No, stop. No.
No, thank you, I won't.
Many people in my life have said and looked me point blank in the eyes and been like, I hate the way you describe things.
I'm on board so far. I love the meat hook maggots.
Well, listeners, let us know in the comments. Now, we've described sort of anatomy. I assume those are all the main parts?
That's the main parts, right? I mean, you get into the abdomen, and the main thing there is that it's more elongate in Nematocera, and it's more shortened and fused in Brachycera, but it's telescopic. There's nothing like happening like in bees where like there's a stinging ovipositor. Maybe. We'll talk about that in the fossil record. Right? But it's nothing crazy going on. All the craziness is going up on the thorax and head.
Sure. So before we leave the anatomy, before we leave the thorax, we hinted at this a little bit already. One of the things that I know, even with my limited knowledge about flies, is a famous thing about this group is their flight capabilities.
Yes.
And you did mention this a little bit, but I wanted to give you a chance if there's anything else you want to say about what makes Dipteran aerodynamic movement, their flight capabilities, so unique.
So what's interesting is that, and we have to talk about it a little bit, is like the venation of the wings. Is that, go back to your dragonfly episode, you talked about it a little bit, but if you think about a dragonfly
181
wing, it's like a pane glass window, right? It's full of veins, it's really rigid. When you get to flies, the wing venation's really reduced, and the wing venation actually assists with certain behaviors and movements. So there's a vein that typically you would see go from the base of the wing, terminate at the tip. But instead in flies, it curves up to the foredge, and just this curvature helps them hover in air, right? So it allows them to hover like a helicopter just in space, right?
Yeah, and which is a thing, I believe, that is rare among insects. And flying animals in general, being able to hover. We talked about that in the dragonflies episode, too.
Exactly.
That dragonflies can do it, and flies can also do that. That superpower among superpowers, the ability to float in one spot in the air.
Exactly that. And think about, dragonflies had to have 4 wings to do this. Flies only need 2. Exactly.
Yeah.
But the way they fly is kind of the same way a lot of insects that are known as flyers do. It's not so much that the muscles are moving the wings, is that the thorax is deforming and reforming, and they're flexing it rapidly, which is how they maintain flight. But mainly it's the halteres are the big thing. Like, we can mess with the halteres, and we have messed with them in the past, where, okay, we're going to snip the right haltere, see what happens. And then the fly starts moving in a circle, to the right, right? You snip the left one, it moves to the left. You snip both of them off, and it has no way to orient itself in space. Yeah, they're so reliant on these organs and they're so specialized that without them, it's like us without GPS nowadays. They don't know where they're going.
That is a cool concept that these allow them to do the insane flying. They're like one of the things I see referenced often is the fact that a fly can land upside down on your ceiling is ridiculous. We're used to seeing them do that, but that is them flipping 180 degrees and then landing on an inverted surface. But then if you remove those things, they basically can't fly.
Yeah. It's like those Battlefield 6 clips where the guys are flying upside down in the jet. And I don't know how you do it. I don't know.
Well, and I was going to say, actually, because I've also heard that flies, one of the things that makes them unique is that they can fly backwards and they can fly upside down. And given that we have a fly expert here, I wanted to ask, how true is it that A, they can do that, and B, that is unique among insects?
I've seen them do it, right? I've been out in the
That's
field.
good enough for me.
I've literally been at like a carcass, and there's flies there, and it goes up, and then it's like I try to sweep it at them, and it just goes backwards. But unique among insects, there are some insects that can kind of move backwards a little bit. It's not the most graceful, right? Because if you think of there's some butterflies that they come to a flower and they're hovering there and they're flapping those big wings and they can kind of move backwards from it, but they're not moving at speed like a fly would.
Right.
There are beetles that accidentally go backwards because beetles are just a tank with wings.
Right.
And if they try and fly, they're like, I'm going to go over there. And then they start going backwards because the weight of their body is pulling them backwards. Yeah. Like, it's Optimus Prime with a jetpack. Like, it does not work.
Ironmonger taking off.
Yes. It is really interesting because, like we said, we did the dragonflies episode and we did the fly. Now we're doing flies, and these are maybe the 2 groups of insects that are famous for their flight capabilities. That they are really exceptional among insects, And it's fascinating to think that they are doing it not only in very different ways, but also for different purposes.
Yes.
We described in the Dragonflies episode, we talked about them like attack helicopters, right?
Mhm.
These are aerial predators, whereas flies, to my knowledge, tend not to be predators and tend not to hunt in the air either. So let's segue into the next part, which is tell us about how flies live, their typical habitats and diets. Feel free to correct the thing that I just said if I was wrong.
All right. So there are some predaceous flies.
Okay,
Cool.
fantastic.
I'm just corrected right off the front, right there. So you've got robber flies, you've got dance flies. These guys will hunt down prey. They'll take prey out of the air.
Oh, cool.
Robber flies are these really relatively robust, like they kind of look like this in between of like a brachycera and like a mosquito, where they've got kind of a elongate body, but they're big, they're bulky. Looks like they've been doing shoulders, and then they have these really pointed mouth parts, and they're really good predators. But they'll also rob other insects, hence robber flies, of their prey.
Oh, cool.
And then there are some dance flies that, I mean, I would classify parasitism or parasitoidism or hyperparasitoids as a type of predator. And
Sure.
so they will land and parasitize various insects like ants, things like that.
Mm-hmm.
And so, they're taking prey as well, and there's various prey in them. As for habitat, though, as I said earlier, these things are everywhere except the deep ocean.
Mm-hmm.
Mhm.
And because they're whole metabolists, we touched upon a little bit, we've got niche partitioning going on.
Right. The larvae and the adults are living
Yes.
very different lives.
Very different lives. In the larva, we've got herbivores, we've got scavengers, we've got decomposers, there's predators, there's parasites, hyperparasites, and you get specialization within that where the herbivores are also galling, they're boring, they're leaf miners, they're scrapers, they're filter feeders, they're feeding on all sorts of things.
Cool.
Blood feeding is common, saprophagy, phytosaprophagy, right? These things, if there is something to be eaten, flies have evolved a mechanism to do it, just in the larval
Totally
form.
makes sense.
I was just going to say, is there anything that flies don't eat?
Not that I can think of. Like, honestly, there's wood boring ones. There's ones that bore into the wood to hunt wood boring larvae of other insects.
Yep.
Like, it's
Fantastic.
they're everywhere. They're all sorts of things. One of the most common feeding guilds, I guess you could say, is our detritivores. Any sort of detritus, any sort of organic material, they're eating it.
This is kind of the famous thing about flies.
Yeah.
Is
Yeah.
they stick around decomposing matter. It's why we associate flies with filth and dirtiness.
Exactly.
Because they hang out around decomposing things.
One of the papers I read was talking about larval feeding mechanisms and methods and guilds, and how we see a trend of larvae being aquatic or living in enclosed spaces, which encapsulates everything from subterranean to corpses,
Right.
Yep.
because that's an enclosed space, right? And I was like, that's a very nice, polite way to put that in a scientific
Yes.
paper.
They're indoorsy.
And then the adults are free living,
Mhm.
Yes.
right? So that's mainly the differentiation, right? Larvae are aquatic and enclosed, and the adults are free living and out in the world. But again, there's some overlap that can happen. Like I mentioned here, blowflies, flesh flies, a lot of those ones that are famous for feeding on carrion. The adults might be there at the same time, but the larvae are there because the larvae, while they're eating the meat, the adults are sucking up the juices.
Well, it feels like in some cases with flies, there's got to be situations where, like, a dead deer, there's so much to go around that's so much material for them that
But
you
one fly that would exploit that deer, a single adult fly can lay between 300 to 500 eggs
Mhm.
okay,
on
yeah.
that fly, right?
Mm-hmm.
And then when you look at things like mosquitoes, mosquito larvae, a lot of what we refer to them as knothole breeders. So the knothole in the side of a tree that would like collect water, the mosquitoes can reproduce in that. They just need a minimal amount of space, and whatever particulate matter's in there, that's what they're feeding on. That's why they're so good at synanthropic environments, being with humans and exploiting our things, because that knothole is also the tarp covering the project that your dad said he would get to 5 years ago, but it's still collecting water. Right?
Yep, the old toy you left out in the yard, the bucket that gathered some water.
It's the bottle cap that's flipped over. They can reproduce in that.
Yeah.
And so then they're just feeding on this basic particulate matter. And then the adults come out and the males are like, cool, I'm going to go find some flowers. And the females are like, I want blood.
Yes. Well, and it feels like that's also got to be a big part of why flies are so diverse and numerous, is that the world's bigger for them. Like there's more potential environments for flies than there are for something our size, so you can get just species on species in just microcosms.
Yeah. Oh, here's a question that I didn't put in the outline either, so we'll see if you know the answer. What is the size range of flies? How big is a typical fly, and how big do they get?
So the largest ones really are like horse flies, deer flies. There's a specimen we have in the lab that I would say it's a good solid like inch.
Yeah.
Right. In length, right? And it's a robust fly, but they can get tiny. They get real tiny. They can get in the millimeter range. Right.
Yeah. Yeah. A group of animals that caps out at about an inch long that is a group that is living a tiny existence.
Yeah.
Hold on. I want to look up what's the world's largest Diptera.
Sure.
Because even I don't know.
It was, as you were saying it, I held up my fingers and I went, that's about as big as I'm imagining. And you said about an inch. I went, all right. Yep.
Yeah, I was doing the same thing.
There's one that's nearly 3 inches.
Oh, really?
Wow.
Yeah.
Who's that?
Goromidas heros mididae. That's a big boy.
It sounds like a 3-inch name.
It's a neotropical species. Yeah, it's neotropical. What do you expect?
That makes sense.
Adult males feed on flowers. Females don't feed at all.
I remember many years ago, I took a trip to Great Salt Lake in Utah, and you walk across the big, the salt flats. And I remember distinctly the experience of hearing the sound of what sounds like just the sand blowing around in the wind. And then you walk up to a bird carcass, because there's no predators out there, and a shadow lifts off of the carcass.
Yep.
And I realized that those are not sand grains. Those are brine flies.
Yep.
Yeah.
Which I assume are true flies.
Yes.
Which are it's just a carpet of these tiny, tiny flies that look and sound like sand grains hanging out on these carcasses.
This is why Stephen King wrote about flies so much in his books. It's terrifying. So world's largest fly is a Midas fly, 2.8 inches. These flies are neotropical, and they are wasp mimics.
Oh, cool.
They are Hymenoptera mimics. Yeah.
Interesting.
Everything has to bow to Hymenoptera. Everything is scared of Hymenoptera.
Yep.
That's just how it works. But the thing is like, as I said earlier, the males are taking a nectar meal. The females are not taking any meal at all. Almost all flies actually are fluid feeders. All adults, right? Like I said, there's no actual chewing, scraping mandibles going on. You've got piercing, you've got sucking, you've got lapping, sponging. Some of them do this wonderful behavior that I wanted to tell you guys about called bubbling.
Bubbling.
This is going to be gross. I can tell this is going to be gross.
A little bit. They do this with honeydew and nectar and other fluids, right?
Okay.
But it can be done with blood, where it's mainly in brachycerans, because they have the mouth parts for it, where the fluid they take in, they then regurgitate and make it into like a bubble, like you would chew bubble gum, and they blow a bubble with it multiple times to evaporate the liquid and reduce the volume of the liquid meal they're taking in.
Wow.
And then also evaporative cooling. So this reduces the amount of liquid they're taking into their body, and it helps cool down the body. So it concentrates the nutrients.
What?
Yeah.
That's
very cool.
awesome.
Thermoregulation by feeding method is fascinating. That did not come up in episode
Yeah.
179. That's an addendum.
Uh-huh. Bubbling is not something you talked about in there?
We sure didn't. That's why we got you on the
Yeah.
podcast.
Yeah, I don't think you did. It's one of those things that's just a very interesting and odd behavior. But some studies have shown that when like the ambient temperature goes up, the more frequent the bubbling behavior occurs.
Yeah,
too.
it's like
Interesting.
panting, effectively.
Oh, now I'm just
Yeah.
gonna hear like flies panting like dogs in my head.
Yeah, and just a big bubble.
Yep.
Ugh.
That's wow.
So we've got this incredible diversity of flies. Listeners, let us know if we didn't mention your favorite member of this group.
There's so
I know
many.
we'll mention more. I do want to take a moment and zero in. So, Diptera, broadly speaking, are flies, and I get the impression that basically every group within this order, they're some kind of flies.
Mhm.
Mosquitoes have their own special name, and they have their own special place in sort of our cultural relationship with insects. They were
Yes.
also requested by a bunch of our requesters for this episode
Mm-hmm.
specifically. So I do want to take a moment, and we've already covered some of it, but what makes mosquitoes distinctive and special, or what doesn't make them distinctive and special? How are they? Do they deserve their own special name?
Well, the reason they're so special is because they are the number one killer of humans.
Sure.
That's it, right? They are, out of all the Nematocera, right? Nematocera, however you want to pronounce it. Don't at me, Dr. Brundage. My boss literally said, Brandon says it wrong to a class we taught the other week.
Well, you are around vertebrate specialists here, and therefore no one will argue with you.
No.
So they don't know. You guys don't know. I can say however I want. Nemis. Anyway, out of all of them, the flies, these are the ones that when they bite, they're piercing the skin, right? They're taking a blood meal. You can't feel it, right? Until after the fact, unless you catch them. It doesn't hurt. And then maybe a pathogen gets transmitted.
Yeah.
And those pathogens are really bad.
Yeah.
Right? And they're the most prevalent, right? There are some other flies in there, like black flies and the tsetse, that can transmit a pathogen, but they're maybe transmitting like one, maybe two. Mosquitoes have this whole host, this arsenal of things that they're transmitting. And that's what makes them so unique, is there's no other like fly that's doing that. The only other arthropod, not insect, arthropod, that even has an arsenal that is equivalent is ticks. They're the only ones that carry as much as they do. The only reason mosquitoes get more attention is because they can fly and move around. If ticks could fly, don't like that. Don't like that thought.
We're moving to Mars.
Yes.
Yep.
So because they're taking a blood meal, because they're putting their salivary enzymes in, because they're transmitting these pathogens, that's what really makes them these unique things, is they're arbovectors. They're carriers and vectors of these pathogens. And honestly, we really only found that out within the past 120 something years. We're coming up on like 120, right? Medical entomology figuring out that mosquitoes could transmit pathogens happened like 1905, 1906, 1907. Around
wow.
that. Yeah,
Yeah.
it's relatively new.
Mosquitoes there is something extra unnerving about, because we get this with ticks, we get this with leeches, animals that are specialized parasites of large animals like ourselves. Mosquitoes feel like they are one of the very few living animals that are extremely specialized and extremely good at hunting humans.
Well, I would posit, because I haven't seen this in the literature, but you guys did talk about this a little bit, dragonflies, how there's like this kind of inherent genetic fear of dragonflies in other insects. They see that shape and that's there. I would posit that there's probably, some genetic behavior encoded in us to be afraid of mosquitoes.
Yeah.
When we hear that noise, and that biting, we respond, very viscerally. We see that behavior in other animals regarding flies that harass them. So there's certain tabanids, so deer flies, horse flies, all those biting flies, that if a cow hears them, they start freaking out. They start kicking and jumping in the air, right? The fly may not even be on them yet. They're already doing that behavior. It's kind of, I would feel that there's the same type of primordial response in us as humans to mosquitoes.
Yeah.
Yeah,
There
no.
is, just speaking anecdotally, it is a different experience to be bothered by like a housefly versus a mosquito.
Mm-hmm.
Yeah. And I definitely get where you're coming from on that, because like if it was just the fact that it's taking some of my blood, that's not actually that big of an issue. Like unless I let myself get covered in mosquitoes, they are not going to take so much of my blood that it's actually going to affect my day.
Yeah.
Right.
But the fact that when I hear that specific high pitched,
Mm-hmm.
I go, "Where are you?
Yup.
Where are you?" And I'm on edge immediately.
And it's always by the ear.
Yep.
Always right there. For a long time, I was very, and still to this day, I try not to, I don't want to kill bugs.
Yeah.
Right. Even bugs that are bothering me, I try to give them some warning swipes. If they're in the house, I'll take them outside. Mosquitoes are the exception.
Yeah.
Mosquitoes are the one where it's like, listen, pal, it really is you or me.
Oh, yeah.
And that's not a gamble that I'm going to take.
There's no way for us to coexist in this room. Like a housefly, okay, you might fly at my phone screen every now and then. I have to go, stop it. Like, and that's annoying. But a mosquito's like, no, if I let you stay in here, you are eventually going to bite me. That is why you're in here. There are no flowers in here for you to be a male. You are a female. You are eventually going to bite me. So you need to go.
And who knows where that mouth has been.
Mm-hmm.
Exactly.
It is fascinating that they are, because I guess I never really thought about that, but you're right that mosquitoes and ticks are really what sets them apart isn't necessarily the way that they feed or the way that they live, but what they carry inside of them.
Mm-hmm.
That they're just vectors for so many really dangerous diseases.
There's only one other group that I can think of that, again, it goes mosquitoes first for the amount they carry, then it goes ticks, and ticks can carry more, but it's their mobility that limits them.
Right.
Fleas.
Yeah.
Right. Yeah.
Fleas and then lice, right?
Yeah.
And among all of those, mosquitoes can fly.
Exactly.
And we've talked about this on the podcast a whole lot, that flight is maybe the most preposterous real life superpower that animals have.
It's unfair.
And a sanguivore, a blood feeding animal that hunts humans that can fly, that's ridiculous. That is OP.
Nerf mosquitoes.
Yeah.
Yes, nerf, absolutely. Nerf mosquitoes.
Yeah.
Well, I'm waiting for that patch to come out.
All those others are like no fun to have on you.
Yeah.
Fleas and ticks are no fun, but I cannot be swarmed at a moment's notice while stepping outside by any of them.
Yes. I can throw a tick across a field and I'm never going to see that tick again.
Exactly. Yes. With mosquitoes, like, did you go outside during summer in Louisiana? You are now surrounded and covered by mosquitoes, and it's that instantaneous access that they have to us is also, I think, part of where that, like, why it's so unnerving that you outside, then you're not actually safe from mosquitoes.
You're not safe. Everything the light touches.
Yeah.
The only time I can think that, like, ooh, maybe like fleas would be terrifying is if somehow we were forced back in time to around 14th century Europe,
Yes.
and then we walked outside and we're like, no.
Right.
Yes, exactly.
Bad.
Very particular time.
Then scary.
Yeah, so there's not really much that, honestly, beyond the blood feeding, beyond the vectoring, that kind of really makes them these unique things. Because all they're doing is taking what flies do, fluid feeding, and they're just going, hey, I'm going to take a little bit of your blood. And they've been doing that for millions of years.
It really is their relationship with us that makes them unique in our minds.
Exactly that.
That's fascinating.
I feel like with them, there's also an aspect of like psychological, at least for me, the fact that your face is so recognizably a needle.
Mhm.
Like it's not working like a hypodermic. It's not just a hollow tube. It's more complicated than that. But that at a visual, I can go, that's a thing that takes my blood. I've seen it in the doctor's
Yup.
office. I've
Yep.
like it is so instantly recognizable as what it is about to do to you that I feel like that is part of
What-
that very visceral reaction you have of that is a fly with a needle on its face, and the needle is for me, and it wants my blood.
What makes it worse is that needle is in a sheath that's
Mhm.
covered in hair.
Yeah,
just-
hairy needle.
Well,
Don't
and
like it.
actually, I was going to mention, because earlier you talked about, I think, horseflies. You were talking about who have adapted to tank a hit.
Yeah.
That they are, I'm going to be biting big animals. I'm going to get hit. Mosquitoes do not tank a hit.
No, they do not.
Mosquitoes are made out of hairs. Like I was going to say toothpicks, but they're not even made out of toothpicks.
Yeah.
They're so delicate. And so, as Brandon, as you've mentioned several times now, you don't feel getting bitten by a mosquito. That's their defense, is that they
Exactly.
land very lightly. Their bite is not something that you sense. You don't know they were there until they're gone.
hmm
Because if you catch them, that's the end of the mosquito.
Now, I do have a thought in my mind, and I did not go into this yet. And maybe we, this could be something brought up, I don't know, in a mosquito episode. Get the comments, suggest it. Follow-up episode. But when did mosquitoes develop that? Because if they're biting through dinosaurs back in the day,
Mhm.
were they using that same mechanism? How thick was the hide?
Yeah, do you need to be as stealthy?
Yeah.
Right.
But then we get past extinction, we get to the mammals who have thinner skin. Was there a shift over to being stealthy? Something like that.
Yeah.
I will reach out to some colleagues.
It also does make me wonder if, because obviously a bunch of other animals, like you mentioned,
Mhm.
horses have tails and a lot of animals have
Yeah.
ears that they'll use. Other animals will like roll around in the mud and rub up against trees. But I do find myself wondering if parasites of primates
Mhm.
have to be extra careful or extra
Mhm.
stealthy, because you're dealing with something that can at a moment's notice reach to any part of its body
Mhm.
with extreme dexterity.
Yes.
And I don't know if that's
I mean,
putting us up on too much of a pedestal.
yeah, we'd have to
Mhm.
think about, well, if you get like a lice infestation,
Yeah.
right? If you've
Mhm.
had head lice, eventually it starts to itch. But you don't
Mhm.
know upon that initial
Yeah.
infestation. And then by the time you're recognizing it and you're itching and scratching, they're attached to the hairs. You can't get them out.
Yep.
This also made me wonder, talking about like mosquitoes feeding on dinosaurs, do we see what behaviors or specializations do we see on ones that feed on like crocs?
Mm-hmm.
I know that like for a lot of reptiles they'll go for the eyes where it is the easiest access. But yeah, like are there specializations or like special behaviors of how they aim for animals like that are going to be harder to get at?
Ectoparasites and arbovectors. That's the next. That's
Yeah.
So
Yeah.
put in your request now for just more Brandon. Stuff Brandon wants to talk about. Well, having gone into gross detail about the modern diversity of Diptera, right? Flies, mosquitoes, all the many, many different types of flies. After this short break, let's move into the past and talk about the fossil record. We've alluded to it already. There is a deep evolutionary history of these animals and some very famous fossils. So stay tuned after this short musical interlude, and I will ask Brandon to explain what fossil flies are like.
Yeah.
So, in the first half, we talked about what living flies are like. Now, Brandon, I would love for you to tell us, what are fossil flies like? What do fossil dipterans typically look like?
Well, they look like flies. That's
Great.
the easiest way to say it, right?
Everybody, thanks for listening.
Yep, there it is. There's the episode. We can end it right there. These aren't like hell ants, right? They don't have weird vertical mandibles. they're flies, right? They look
Mhm,
like
mhm.
flies. They've looked like flies for about 250 million years. The earliest fossils that we have are, and correct me if I'm saying this wrong, Anisean?
Yes, Anisian. Yes.
Anisean,
That's Triassic, isn't it?
Triassic, yeah, right? And it's the splitting of the Triassic even further in this different times.
Yes.
They're Triassic.
Yes.
And they're it's from a French fossil site. It is like other fossil sites will in Europe will be like, oh, we got like three fly wings. We got like maybe two over here. And this fossil site's like, we have 80. And it's like, oh, that escalated real quickly. Unfortunately, though, a lot of fly fossils are wings, just wings,
Right.
right?
Yeah, this came up in dragonflies as well. That
Yeah.
is typically what you find in the fossil record.
So the whole thing is, as I alluded to in the first half, and talked a little bit about, venation's really unique to flies. We can tell that they have this fly venation in these wings even back then, right?
Hmm.
There's been some like molecular dating and like the hypotheses of when flies might have emerged, and that puts it around 265 million years ago. So having these wings with these fly characteristics that are kind of, in the Triassic period fits that timeline that we're seeing.
Sure. I imagine that these, or especially early fly fossils, tend to be individual wings preserved in sediment, the same way that you imagine a leaf or a feather in
Yes.
sediment. It's
Yeah.
a fly wing.
Yeah. Our two fossil types that we see are like compression fossils
Hmm.
and then like amber.
Yes, amber, of course, the famous way that we find
Yes.
fossil insects.
The very like real first one from this particular site was published about in like 1994 by Kurzaminski, and he's the one who identified it and gave it its name of Gravogelia arzivaleriana.
Okay.
And this is like our oldest. This is a fly wing. We know this is a fly. And as you talked about in your Odonata, dragonfly one, the wings preserve, right? There's
Mhm.
not a lot of tissue in there. There's not organs that can rot. It's just chitin.
Yeah.
That's it. It's just chitin. The whole thought, though, at least for me, paleo entomologists can say I'm wrong if they want. But when I think about why these are getting fossilized, and maybe it's a single wing, maybe it's a pair of wings, is that a lot of predators currently to this day rip the wings off of flies. They're
Yep.
non-edible parts. So if you
Yeah.
have something eating a fly on the fly,
Eh, eh.
they're going to rip the wings off. Those are going to drop down, and some of them fall into the perfect place to get fossilized.
Yeah.
Well, I imagine even if they aren't actively hunted, a dead fly, scavengers and decomposers are going to go after the body and they're going to leave the wings
Yeah,
the same way that, other examples of the hard parts not being eaten that I can't think of right now. But this is, well, it's like how you see those pictures of hyenas sticking their heads inside the stomach of a
Mhm.
carcass because it's softer and easier to go after than the
exactly.
skin.
When we do get Diptera and amber, though, then we'll get some of them, within the problematic amber. We do get them in
Mhm.
Burmese amber and stuff like
Sure.
that, which you guys have talked about the issues of that in past episodes.
Yes.
Yep. Myanmar amber, which is the Myanmar amber. It's such a shame that it's become controversial because, in addition to the human cost of the controversy, that this is the source for Cretaceous amber.
Yeah.
Basically, all the famous amber specimens that you can think of are from Myanmar amber, the mining of which has very unfortunately been tied up in geopolitical situations that are very negative for certain demographics of people.
Yep.
But we have also learned a lot of really important scientific information from specimens preserved within this amber.
Yeah. So that's, there's a lot of amber that has these specimens. And when we do look at them and we do CT scans and things like that, we can see the venation of the wings, right? That's one of the first things we look at. We look at the venation. Oh, this is fly wing venation, right?
Sure.
And then in the very older specimens, right, where we do have either amber or compression fossil of a whole body, we see reduced hind wings that are going
Mm.
either already as halteres or on the way to be halteres.
Okay. Interesting.
So there's some like transitional fossils that we have of flies, which is very interesting. And I'll talk about that in a little bit. I'll keep going. Sometimes when we have like these full bodies, we can also reconstruct other parts using CT scanning that also indicate this is a fly, not just halt ears, not just wings, but even the genitalia, right?
Yeah. Yep.
Yeah, I made this comment to Brandon before we started recording that my understanding is that paleoentomology is 90% wings and genitals.
Yep.
That's how you identify fossil insects.
There is a thing in entomology, which is weaponized genitalia, and
Sure.
they are so unique amongst insects that things have spines in certain places and curvatures that, again, like ketotaxy, we can look at the genitals of an insect and kind of know what species or what realm we're in.
Yes.
When you get a fly in amber, can you count the hairs?
I haven't seen any paper talk about that. I imagine they are avoiding that at all costs.
Sure, that makes sense.
That sounds horrific.
Well, it also seems like a structure that could probably get damaged fairly
Sure.
easily in the fossilization process.
Well, here's the thing. They have specific pores. So even if the hair is gone, the pore is there, the site is there, and you're not off the hook.
So there's really no excuse.
No.
It's just a bunch of scientists saying, I did fossils specifically so that I wouldn't have to count the hairs on a fly.
And they're going, where's a grad student? Give me a grad student to count this.
Yep.
It seems like a great citizen science project.
Exactly.
You CT scan it, you put it online.
Oh, yeah.
You let people count the hairs.
So we have these adults, right? And I'm mainly talking about like our most ancient ones, right? Triassic is where we have our first emergence of Diptera. But I've mainly talked about adults here because it's really hard to fossilize squishy juveniles.
Yep.
So the only ones that we really have fossils of are Nematocera.
The one with the hard head caps.
Hardened head capsules. Some of them have sclerotized bodies. Some of the oldest ones that we have are chironomids, right? So chironomids are midges, non-biting midges. And so they have aquatic larvae. And so they get into that sediment and their body is relatively sclerotized and they're filter feeders. They're taking in particulate matter. So we have fossil record of those. And again, it's kind of that circa Triassic, early Jurassic.
Sure. So we're around 200 million years ago, maybe a little bit older. It sounds like flies are getting started around the same time as dinosaurs and turtles and lizards.
Yes. We start to see kind of this like differentiation occur around that time because the most ancient relative, I'm going to skip ahead to one of your questions of what they evolved out of and what they're most related to are scorpion flies.
Oh,
this is a group called Mecoptera. And we have Mecopteran fossils from that like pre-Permian extinction. So they were there with like the first iteration of like gymnosperms. And they're adapted to pollinating and feeding on gymnosperms. And if you don't know what a scorpion fly looks like, imagine like a really kind of long proboscis, but it's like the face is elongate, like a who, like a who from Whoville, right?
Yeah. Scorpion flies, no space. They
No space.
They are not Diptera. They are a separate group.
Mecoptera, it is a separate order. They're like better one. They look like anteaters. The face looks like an anteater. And then the abdomen, actually, they have the ability to curve it up like it's a scorpion stinger, right? And but they have no venom.
Yeah.
But they're adapted to feed on like gymnosperms and stuff like that. And so then you have dinosaurs start to arrive on the scene. And we do have some transitional fossils of Mecoptera, Diptera, like right in between.
Oh, cool.
So we have this proto-dipteran. We actually have two. One is called Choristotanidiris nanus and Permotanidiris abliptus. Not to get into the weeds too much, but their wing morphology, again, is what differentiates them. So we have this Mecoptera wing venation, and then we have Diptera wing venation in that as well. So they have two different
Oh.
insect orders with very unique wings, and this is the middle ground. It's a bit of both.
Fascinating.
Yeah.
So if scorpion flies, like you said, those early scorpion flies are specialized for feeding on, conifers, gymnosperms, these other
Yep.
plants, does that suggest that the earliest true flies were herbivores?
So that's what we see in the fossil record, is that the most basal group were herbivores.
Okay.
And they were adapted to doing this. There's some thought that they were also feeding off of honeydew produced from these scale insects and hemipterans at the time that were more adapted to feeding on the gymnosperms and conifers. So those guys have really piercing, sucking mouth parts. They're taking all the liquids out and then exuding honeydew. And so the ancient true flies were feeding on that and other honeydew that they could access. And they already have this kind of straw like mouth that's built. So over time, they start to evolve and adapt it more specialized. And now you've got these large walking meat sacks that, hey, they've got some goodies inside of them. Maybe if we pierce that skin, we can get to it.
Right.
Mosquitoes. So what was really interesting going into this was the fact that, no, we know Diptera came from Mecoptera, right? We have the transitional fossils. Our oldest Mecopterans from the Upper Permian, like it's there.
Cool.
But we then have to look at other factors in the fossil record. One that we call the brachycerization. That is a mouthful.
Yeah.
Of flies.
Right. The transition from that mosquito crane fly like shape
Mm-hmm.
to the more familiar housefly style.
Because when you look at like this Triassic, Jurassic, our most common fossils are, chironomids and chaeoborids, which all belong to this group called Culicomorpha, which encompasses mosquitoes, chironomids, the biting midges, which tepulids, crane flies, phantom crane flies, drain flies, black flies. All of them are within that group, and they're there. But how did we get from these spindly, thin mosquitoes to the kidney bean with wings?
Yeah.
Right? And so we move from kind of that Jurassic, Triassic, but we don't see a lot of this radiation adaptation till the Cenozoic. We start to see brachycerization in Jurassic to Cretaceous, but nothing blows up until Cenozoic.
Huh.
Okay. Interesting.
Right? So we have a interesting one. So this is exciting fossil, right? Because that was a prompt that you had for me, but also part of this brachycerization weird change from Nematocera to Brachycera. And it's a fossil of what's called an oestroidea, right? Oestrids include botflies, blowflies, flesh flies. You know I'm biased.
The gross ones.
Right, a little biased. But these guys look like dragonflies.
Oh, interesting.
It's weird, right? So they have this elongated abdomen, which we don't see in Brachycera. But then they have that short, stocky thorax, and then that bulbous brachyceran head, right? Where if you think about dragonfly heads, they're bulbous with large eyes. This fly is bulbous with large eyes and an elongate abdomen and large forewings. It doesn't have any hind wings. It's got halteres.
It's like a two-winged dragonfly.
It's like a two-winged dragonfly. It's wild.
Do they seem to have been predaceous?
So no.
Oh, okay. Well, yeah, I was gonna say, did this group of flies go through a dragonfly phase where they were aerial hunters on the way to being flesh eaters?
Maybe. So this was one where the mouth parts appear adapted for sucking and like consuming liquid foods from like plants, like nectar food.
Okay.
Right. So their arrival on the scene is at the same time as like angiosperms and flowering plants. So they show up there. They look like dragonflies, but they're taking a nectar meal, right? But also they have a thorax. I mean, not a thorax, an ovipositor, the tip of their abdomen that is sharp and pointed, and
Interesting.
elongate that would indicate some parasitoidism is there. Like they might have been a hyperparasitoid.
Yeah.
Interesting. Would it, because I know some animals use that for piercing into plant tissues
Exactly that as well. That's the
to lay
other
the
thought.
eggs.
So the
Interesting.
thought is that either it laid its eggs in plant material or is a hyperparasitoid and used an ovipositor for that.
Yeah.
So it's one of those things. Was this for plants? Was this for parasitoidism? We can't really be sure because, making inferences about lifestyle and breeding is really difficult in this. There's a quote from this paper that essentially says we don't know because this mixture of characteristics on a fly has never been there before and
Yeah.
seems nearly impossible.
Yeah.
This is a group of flies doing something no other flies do.
It's so weird. It's so weird. So
Huh.
this was, I'm correcting myself. This wasn't the estrid. This was Aeromochaetidae. Aeromochaetidae.
Sure.
And these guys are an ancient group that is now extinct. So
that might represent that bridge
yeah.
between the mosquito shape.
So this is the bridge one. They showed up in the Mesozoic, and then by the extinction, they're gone.
Gotcha.
Huh.
They're gone, but we've seen the radiation of the stout body form of modern flies. Very cool.
So it's not listed as a transitional fossil, but it looks like it's a transitional fossil.
It's
Cool.
a really interesting conundrum trying to interpret the lifestyle of an ancient fly that has an anatomy unlike any living flies.
Yeah.
Because like we said, modern flies kind of do everything.
Exactly.
So there isn't anything out of the question. It's not like we found a fossil snake and we were like, did it eat plants? No, we know it didn't eat plants. It's a snake.
Exactly.
That's not a thing snakes do. This is a fly. So like it probably didn't live on the ocean floor. Other than that, it's really hard to narrow it down.
It's up in the air because those mouth parts, like, they could be used for consuming fluid, but also, like, what is that fluid?
Right. Yeah. There's a lot of fluid out there.
There's a lot of things. Is it nectar? Is it rotting material? We are just fluid encased in meat. And then the ovipositor is the weird thing. We don't see like a sharpened ovipositor like a hymenopteran ovipositor. We don't see that in flies. We've got parasitoids, but we don't have that. That's a weird thing.
If any flies had pointy ovipositors, you would have talked about the abdomen early in the episode. That's why I asked. I was like, are there any cool ovipositors? No, there's not.
Not really.
Apparently
no.
there used
like,
to be.
They're telescopic, like they can like them out, but that's about it.
Crazy.
Yeah, so there's these transitional fossils that show us when that occurs. And so you also have ones like in the Upper Jurassic, which is really cool. This was also from that same French site, right? Where it's Elena Lukashevich. They found some fossilized pupa that most people think, oh, well, we can't really identify pupa. There's certain characteristics. But these pupa from this period of time had the same, what we call trumpets, right? So these are ways for the insect to breathe while it's encased in this housing.
Right. It's like a little breathing tube.
Yeah. The exact same trumpets that are widened respiratory horns that we see in extant species to this day, living species to this day, in the group Limoniidae. So even all the way back, they're still using kind of the same respiratory apparatus when they're pupating as they are today.
Very cool.
And these are ones that it's most likely the larvae were aquatic because the pupa that they found, it kind of indicates it was in like a semi-wet, muddy kind of environment, because that's also how the pupa of today use those trumpets to breathe in that semi-wet environment.
Sure, like a reed in a pond.
Exactly.
Breathing with your breathing tube.
It's just these little fly ninjas underwater with a breathing tube waiting. Yep. And then after that, right? So that's kind of really where we get with that, Triassic, Jurassic. We get kind of into Cretaceous. There's some stuff there, but it's nothing that's really like, hey, this is brand new. It's like, no, flies are established by Triassic to Jurassic, right?
Sure.
That's really where things are. And then after into the Cenozoic, that's where you start to see this radiation outwards, because now we have flowering plants and we've got all these niches that are open. We've had this extinction event
Yeah.
and things just go nuts.
I would have to imagine that a mass extinction would be a good time to be a certain type of fly.
Yeah. Yeah.
We've talked in the past about ferns, which are noted in some cases it seems like ferns do really well immediately after a mass extinction. Certain fungi might do really well after a mass extinction. I would imagine that carrion insects had a great time, at least in the early stages of a mass extinction.
So you would think.
I would think that.
You would think that. However, our carrion feeding insects, the families that we know today, that we have a lot of the evidence for, do not show up until after.
Oh, interesting. So they
Yeah.
weren't around to enjoy all of the T-Rex steaks.
They weren't around.
Mm.
So our calophorids, our sarcophagids, a lot of the muscomorpha that we consider are big carrion feeders, those families didn't get established till the Eocene.
Wow.
Interesting. It's really fascinating, I think, to compare the trajectory of different insect groups.
Yeah.
This is the third insect episode we've done on the podcast about a specific group of insects. And dragonflies, the dragonfly archetype was firmly established in the Carboniferous period, like way early.
Yeah.
And then eventually they transitioned into more modern dragonflies by, I think, the Jurassic. So that's a group of insects that basically became modern, essentially, way early on. And in the ants episode, we talked about ants seem to have really come about in the Cretaceous period. So it was a much later. And flies, you've got that they were flies by the Triassic, but then they weren't really our modern style of diversity.
Yep.
Until it's really interesting how different groups of insects have these different trajectories over time.
Oh, yes.
Yeah.
And like one of the things to consider as well is that this is always changing for flies and insects. So like there was one like carrion fly fossil that was mentioned in the literature. It's relatively famous. It's Cretiformia fowleri. And this was one of those that like, oh, this is an example of a calophorid fly from the Cretaceous. Except when we do more studies on it, or like, ooh, it doesn't exactly fit in with Calophoridae or Muscomorpha or any of these other groups. It's kind of this homeless brachyceran fly right now. So there are kind of these characteristics that what we'd call these caloptrate flies, which are underneath the wing of a fly, there are some of these flaps, right, that are called calopters that protect the halteres.
Okay.
Right.
Yeah.
Okay.
So we call them caloptrate flies. A lot of those caloptrate flies are your carrion feeding flies. So here we have a caloptrate fly. We don't know where it fits in. It might be calophorid. It's somewhere in there. So it could be carrion feeding. It could have been carrion feeding for the extinction. But the modern families that we have confirmed fossil records of, not really at that time.
Interesting.
Yeah.
That, once again, so cool to learn that this iconic feature of this group might be a relatively recent development.
Yeah. Well, and it also raises, as we often like to point out, that like, does that mean that during the time of the dinosaurs, a body did not have that typical buzzing soundtrack the same way it does today?
Yeah. Was it more like beetles and stuff?
Exactly. Yeah. I'm sure there were other things there, but were they buzzing around or were they landing? So there was not this that you are so used to hearing when a dead body's nearby. It was that not the sound of a carcass during the Mesozoic?
now I'm going to think about every dinosaur media cartoon or something like that having flies around dead dinosaurs and being like, that's wrong.
The first image that came to my mind was Jurassic Park 3.
Yep.
They come upon the carcass. Now, to be fair, that is taking place in the modern world where you would have flies.
But those flies were all going, oh my goodness, this is new.
What is this?
Right? Like, this is one of the things that, in my mind, likely we'll cover in a beetle episode.
Sure.
Yeah.
Because
absolutely.
there are carrion-feeding beetles that we know the lineages are Jurassic, Triassic, like they were established then.
Listeners, if you'd like us to bring Brandon back for a 6-hour-long episode about beetles, let us know.
We could do it. We'll marathon it.
just do a all day Twitch stream of
Right? We'll do a Q&A about it.
Yes,
Right?
just talk about beetles. Just name every beetle. Now we did it in the first half, so I want to do it again back down here in the fossil record. What about mosquitoes? Are there famous? Because the image of a bug in amber, the image of an insect in amber is the image of a mosquito preserved in amber. But that's because of Jurassic Park. And my understanding, and I could be wrong, is that we don't actually have a lot of fossil mosquitoes.
We really don't.
Yeah, which makes a ton of sense because even among a group of very delicate insects, mosquitoes are extra delicate.
Just so fragile.
And you're looking at something that they're blood feeders, right? To get caught in amber, you have to be spending the majority of your time on plant material.
Right. No amber on a dinosaur.
Well, female mosquitoes are blood feeders, right? So that whole thing of like millions of years ago, a mosquito landed in some amber. Like, no, that is a D1 million roll. Okay, like maybe there's one out there that we haven't found yet. But mosquito pupa and larvae, those are the ones we have more fossils of because they're aquatic and they're going to fall into that sediment and they're going to get compressed and collected and stuff like that. We have more of those. And the mosquito larvae look like mosquito larvae, right? So they have this enlarged head capsule, they've got mandibles, and they have this slender body with gills or a snorkel on their butt, and that would stick out of the water and they can breathe and move around with that. We have that. There's one from recently discovered 99 million years ago, I believe it was, something like that. So we have those, but the dino DNA, not so much.
So do we have any sense of, because as we've discussed, male mosquitoes are plant eaters, right? They're eating plants. Larval mosquitoes are eating something different. I am getting a corrective finger pointed in my direction.
So, this is a fun thing I found out.
Oh, I do know where this is going because I think we talked about this in the news. Maybe I'm having a flash of memory.
Male mosquitoes, some of them did feed on blood during that period of time. Some of them did. So there is some fossils that I found, fossil records from around this Triassic, Jurassic period of time where it's a male mosquito in amber. So you know it's nectar feeding. But the dentition on the needle and the palps at the tip indicate that it was also taking blood meals. Right?
Which really throws a wrench into the nice, neat story that I was going to say. Does it, presumably it makes sense that mosquitoes started out as plant feeders, and then at some point along the way, they evolved this habit of the females will take blood. But if there were males in the past taking blood, then that idea is out the window, and who knows what they were doing.
So this gets into a weird thing where if they evolved from Mecoptera, which are adapted to feed on gymnosperms and conifers and these seeded things, and then they evolved away from that to have these really sharp proboscis that could pierce skin or pierce into this plant material to take the phloem out of the plant and drink that liquid. Well, it's a hop, skip, and a jump to blood. But then you have flowering plants happen, and you have this reorientation of now we have nectar available.
Yeah.
Now we have nectar,
Yeah.
now we have pollen. And one of the things that we see in modern research is pollen's pretty proteinaceous.
Mhm.
It's got protein in it. And
Yeah.
so some of these plants, some of these flower feeding insects that you would assume, oh, you need protein to develop your eggs. Well, they're consuming pollen,
Yeah.
right? And you need even less protein for males to produce sperm.
Yeah.
So it's likely that just the incidental pollen consumption after we have flowering plants is what just addressed the male protein necessity.
So
So it's
it ma-
possible. We're going to say the same thing, I'm sure,
Yep.
that they might have both been blood feeders, and then
Yes.
angiosperms came around and absolved the males of that need.
Yep, it's possible.
Yeah.
It's very possible.
Wow. It's from plant to blood to then splitting up the duties.
Hmm.
Hmm.
That's such an interesting path.
And of course, this is such a diverse group of animals, and with such a specific fossil record, flies in general, they're only being fossilized in very particular circumstances. So it's also, I think, perfectly reasonable to think that at any given point over the last 200 million years, there were flies doing basically all the things we have flies doing today.
Mm-hmm.
Like there probably were some carrion feeders, and there
Mhm.
probably were some blood feeders, because it seems like it's an easy thing for flies to do.
So
Yeah.
there's one fossil of an ancient mosquito from about 100 million years ago called Priscoculix burmanicus, but it's reminiscent of what's called an Anopheles mosquito. That's an extant species today. That the Anopheles is a malaria carrier.
Oh, yeah.
Priscoculix hypothetically might have also been an arbovector at that time.
Yeah.
So I don't know the literature on it, but dinosaur malaria sounds awful.
Yeah.
I
Huh.
was just thinking, because we were talking before about how a lot of large animals today have long, they have tails that they can wave
Mhm.
around and ears that they can flap to ward off insects. Dinosaurs didn't have that. And it does make me
Mm-mm.
wonder how a dinosaur would have swatted away mosquitoes,
Mhm.
Yeah.
because they didn't have external ears, and they have these long bulky tails that you couldn't use the same way.
Were they taking mud baths all the time?
Mud
Like,
baths were the smaller dinosaurs acting like birds that we see on large mammals today,
yeah.
right? And
Yeah.
something was taking the parasites off of them.
Was it their feathers? Were their
Yeah.
feathers protective over some dinosaurs? Were they able to move the quills around?
Yeah. Could they do like a shiver to shake things and fend away flies?
So, I mean, a lot of mosquitoes are adapted to feed on birds,
Yeah.
Yeah.
and a lot of the pathogens that they pick up are from birds. So there might
Yeah.
be something there.
I do have a book on my shelf somewhere that is a book that is titled "What Bugged the Dinosaurs," and it
Mhm.
is a book
Yeah.
all about what we know of what parasites were around back during the
Yeah.
Mesozoic. And I'm sure this is in there.
Mhm.
I read it many years ago. Well, that's fascinating. Are there any other particularly exciting fossil dipterans or notes about dipteran evolution that you came across that you want to make sure to share?
Yes. Okay. So this was fun. This was another fun one I came across. This was published by Baranov et al. Back in 2019, and they had from Baltic and Bitterfeld amber,
Hmm.
and it was a bibliomorpho larva. So bibliomorpha is another one of those infraorders within Diptera. I believe it's in Nematocera. Yes, Nematocera. So this one, they found larvae like in amber, which is wild.
Very cool. Are these aquatic larvae?
So these guys, so bibliomorphs can be aquatic and they can be terrestrial. So I
Okay,
believe this one
interesting.
might have been terrestrial.
Because there are aquatic organisms known to have been preserved in amber in some cases.
Hmm.
So it's not out of the realm of possibility.
I heard you guys talk about it on one episode. Yeah, that makes sense. But I think this was a terrestrial one.
Hmm.
But this is so distinctly different from extant species that it may not even be an in group for like bibionids. It might have actually been a derived sister group that is distinct, because they could look at the maxillary palps, right? And the mandibles, and they had these extra processes coming off of them. They also had a difference in their breathing apparatus, which instead of like was dorsoventrally like on the sides instead of like being upwards.
Hmm.
And it's called Dinobibio hoffensiorum. And this is the one, actually, I had incorrectly stated with the Oestrad. This is the one where the author was like, these characters should not exist together. This is not
Yeah.
why. Why are you like this? How are you like this? I am
Interesting.
confused. And so they know it's in this bibliomorpha group, but they're not putting it anywhere else and saying this is probably a sister group because it looks like a lineage that evolved and then went extinct where the rest of bibionids continued to live.
Right. This is
Huh.
an ancient lineage.
Mm-hmm.
Very cool.
It's very,
It's great to learn about insect paleontology where you're studying life stages, where some research is all larvae and sometimes it's just the pupa and sometimes it's adults, and you're getting these glimpses at these functionally completely different insects.
There is a preference for adults. It's why so much of the literature is wings. Because when you get into juveniles, it actually gets really difficult. If you think about maggots, think about a whole host of maggots.
Once again, I'd rather not.
Can you tell the difference in species?
No, absolutely not.
Yeah, absolutely not, right? And like even we have like, ooh, yeah, they kind of have like a bump here, and like the opening of their spiracles, how they breathe is kind of oriented this way. But let's let it develop to an adult, and then we'll ID it, and we'll make sure we're correct. You can't do that with fossils.
Yeah.
Right? Where's that in Jurassic Park?
Yeah, right?
Bring back the larva, let it turn into an adult. Oh, then we know what we have. Dinosaur malaria.
It is funny to think that I don't think anywhere in the Jurassic Park franchise did they ever think to resurrect the mosquitoes.
Yes.
No.
Which presumably, if we're pretending that the amber preserved the mosquito, the meal DNA, you'd think it would also have preserved the bug's DNA itself. I'm pretty sure you can't get the blood sample out of the gut of a mosquito without getting the mosquito DNA.
Right.
I mean, the other issue is that was a crane fly and not a mosquito.
The other issue is that DNA doesn't preserve an amber. But, there's a lot of hand waving to be done here.
There's a lot of movie magic. There is one more I want to talk about. This is another fly. It is another oestrid called Mesembrinella cenozoica, right? So we can kind of guess when it showed up, right?
Yep.
We used to believe they're caliphorids, and this is the entire family. We used to believe they're caliphorids, blowflies. Turns out they are the solely neotropical family that is sort of like blowflies, but their own thing. And we're unsure like of their full life stage even to this day in the current era because they're larviparous, meaning the larvae develop inside of the female and then are oviposited, fully hatched and developed.
Yes.
Wow.
And so like we're unsure where the larvae go, we're unsure as to the lifestyle and behaviors because they look like they're detritivores, they're feeding on decaying organic matter, they're attracted to like carrion smelling plants, they're attracted to carrion. So we have this ancient, member of this also from amber. It's from the Dominican Republic, Cenozoic era, and like it looks like there are these types of carrion flies, I'm using that generally, in this region at that time period. And then they likely, instead of caliphorids really being present there, this family is the one that's present there.
Gotcha.
And they convergently evolved the live birth that some modern flies do.
Oh yeah. So like sarcophagids do that, a bunch do that. And
That's so
the
cool.
Sembrunellids do that to this day. But it's in Costa Rica, Dominican Republic. It's kind of hard to track where larvae go from a fly that's the size of a kidney bean. Whoop. And this is a thing that happens though, is they used to be caliphorids, now they're their own family. and this is a thing that's happening repeatedly, is like, ooh, phylogenetics and genetic testing and genome and all that stuff. Once we have the DNA, we're like, ooh, we're shifting again, and we're shifting
Yeah.
again, and we're shifting again. Because all of the identifications I've told you about, they're morphological.
Yeah.
Right.
Yep.
So once we get the genetics, then things shift. That's why if you look up older literature, like Diptera used to be placed with like Lepidoptera as on the phylogenetic tree. And then like some literature said, oh, well, they're actually really close to Hymenoptera. And they were like, one paraphyletic clade together.
Identified phylogenetically has changed over time
Yes.
with genetic data.
Yeah. So with the genetic data, with everything that's happening, things get shifted around so much. It used to actually be you had Nematocera, Nematosera, and Brachycera and Brachycera separate. But now we know Brachycera actually arises out of Nematosera. So that's
Wow.
changed the tree itself. So the more we do, the more work we do, things are going to change.
Yeah.
Very cool stuff. Well, speaking of research on flies, and before we wrap up our fly discussion completely, Brandon, would you mind to just give us a brief insight into what you do with flies?
So, as I've alluded to a lot, I work with Californians, right? I'm a forensic entomologist. So, these are the guys, these are the flies that show up to a corpse, and we can use them for forensic purposes. However, they're also pollinators.
Mm-hmm.
And this is a really understudied aspect of their behavior because a lot of the research goes up into like the 70s and then stops up until about 2016. So a lot of people started switching over to like honeybees and all the major pollinators that you can think of. But these flies, they're still pollinating avocados, they're pollinating carrots, onions, garlic, all of these other plants that are crops and then non-crop plants as well. And so I'm trying to address that gap in the knowledge, but at the same time, bring it back around to forensics. Because if they're pollinators, then when they visit a corpse, they're depositing pollen on that corpse.
Yeah.
But flies only travel X amount of distance. So if I can correlate the pollen that's in their gut, which is on the surface, right? So that means they fed on this plant. This is exactly the insect mediated pollen. They transfer it from the surface to whatever they're feeding on. And there's none of those plants in that given area. Then the fly, it's beyond the fly's range. Then that body may have been moved. That person may have been moved
Yeah.
from a region where that fly was to their new location.
That's
Fascinating.
cool.
Yeah. So addressing forensics, addressing pollination, addressing pollinator syndromes, identifying what plants they're on, and generally being Hodgins from Bones, which I met TJ and he said, yes, you are Hodgins. So there we go.
That is such a fun fun?
I mean, fun for me.
Pretty
Yes.
fun, but you're contributing knowledge about pollination and ecological information that is also useful and beneficial for forensic studies.
Yes.
Yeah.
Which is a very cool overlap and combination of factors.
Oh, yeah. There's a massive overlap there. And one of the things I found out in the field is just like some people are using those flies to this day. Like from the 50s, this one species of fly to pollinate onions. It's the wrong species because they're doing it in Texas and it's a species from Canada.
Huh.
They're like, it dies in a day. I'm like, yeah, it's 105 down here. That fly's used to 60-degree weather. So it's helping to address these gaps and consistent usage of incorrect species, even in agriculture at the same time,
Yeah.
which is very cool. And then I have my, da 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 Law and Order music in the background moment.
You will be delighted to hear that a lot of paleontological research borrows from forensic literature when trying to interpret things like cause of death or diseases and stuff. I don't know off the top of my head if there is very much forensic paleoentomology of that kind of, these are the bugs we found associated with this fossil. Because
Yeah.
I don't know that the fossil record captures that quite well enough.
I mean, these flies are like squishy. As larvae, they're
Yeah.
squishy. That's the issue.
I did have a friend who, when I was an undergrad, she was a PhD student, and her thesis, her dissertation research was looking at taphonomy. So what happens to a carcass as it's decomposing?
Yeah.
And you would have loved talking to her about her project. As part of her dissertation, she collected, I think, 12 deer carcasses that were roadkill and strategically stationed them in different habitats around the outskirts of campus, and then visited them on a regular basis to note what was happening to the carcass, what animals were interacting with it. And she is the person that taught me that there are some butterflies that feed on carcasses.
Oh, yes. Yeah. They need that salt, and they will arrive on carcasses and feed on certain parts. It's not the scope of this podcast. I will be very nice and refrain from going into detail.
So her research she was, I think, more interested in how do the bones end up moving around? What are the evidences of scavengers like foxes and coyotes and stuff? But she was taking note of what the insects were doing, looking for potential information we might be able to find in fossils.
Yeah, those type of studies allow us to note the succession on carrion and corpses, because there's certain insects that show up at this period, and they give enough time, another group shows up, and there's overlap, and then there's like beetles that feed on the larva, and all sorts of things. It's a lot of fun.
Yeah.
Well, fun, I put in quotes.
Yes. Very cool stuff. Brandon, it has been a delight having you wow us all about flies and mosquitoes and dipterans. Before we wrap up our discussion completely, there is one last thing to do. Each episode, we like to answer questions submitted by our patrons on Patreon. If you're a patron at certain levels, you get to submit questions for us to answer here on the podcast. This episode, we have a question from Ava. This is a question that I thought would be pretty fitting for a discussion about flies. Yep. And Brandon, we will welcome you to join us in answering this question. Ava asks, what groups of animals would you call the most successful or the least successful, and how would you define these terms?
Ooh.
This is something that we've talked about a lot on the podcast, that we talk about the success of different groups. Brandon, as a person who studies flies, which I might posit as among the most successful groups of animals, what do you think?
Look me in the eyes, both of you. Beetles.
Yeah,
beetles.
Sure.
Yeah, beetles. There's hands down beetles, right?
Yeah.
There's so many of them. They're everywhere. They're like, 40% of all species on this planet. Beetles, hands down. Least successful, that depends on how we define it.
Yeah.
I would say, not even group, very specifically, anything that needs us to take care of it to keep it going.
Yeah.
So like pandas. Like, I'm looking at you, pandas. Like, you are a bear, you are omnivorous, you are adapted to eating meat and vegetable matter, and you only eat the worst vegetable matter that you're not really good at digesting.
Yep.
Like,
yeah.
Koalas, you can't eat leaves that are not on a stick. I'm sorry. Vertebrates, a lot of us aren't successful. At the same time, though, if I'm going to stay within insects, I'm going to say that Antarctic fly that dies when you touch it. If you die from something that's a little too warm, not even like, it's burning me, hot. Like, this is a nice balmy 70 degrees. I think I'm going to die. That's not that successful.
Yeah. Well, and it's an interesting question asking, like, how do we measure success? Because, like, I think typically, like, number population-wise or number of species are the things a lot of people look at. But I also think that one that you would have to measure in is, like, longevity of the lineage. Like, have they been around? Like, dragonflies are obviously successful, even if they're, like, if they were to go through a period where they dipped. But if they come back, they've been around since the Carboniferous, they've been around for so long. That is an incredibly successful lineage. And that's something I often think about, where you'll get these cool lineages. It's like, yeah, but they actually only last for a fairly short time in the fossil record. They kind of come in and then they go out. And it's like, all right, so they may have been doing fine while they're around, but they ultimately did not have a lot of staying power. They couldn't adjust, or whatever they were adapted to was not a sustainable situation.
Yeah, I think it's really interesting, because I think you could simultaneously define success in multiple ways.
Yeah.
And I will keep us entirely on brand and talk about crocs and snakes. Because I think that snakes are an extraordinarily successful group, in part because they have specialized so much. They are such a specialized body type and lifestyle, but they are also worldwide. They live all over the world. They have for tens of millions of years. They live in all sorts of habitats, despite having sort of restricted themselves anatomically. And crocs are also an incredibly successful group of animals, despite being kind of the opposite in those respects. There are only like 24 living species. They are all kind of doing the same thing that they've always been doing forever. And yet, despite their relatively low diversity, not only are they doing well, they are major ecological forces in every ecosystem that they're a part of. And they've been doing that for 100 million years.
Yes.
And then beetles, which are kind of doing every version, where it's we are one group that has taken on every possible form and habit that a group could take on.
And then some.
And then some, and we live everywhere in the world. So all of these are groups that are very successful, but for quite different reasons.
Well, and like on the snowfly example, that's also one of those interesting ones where, like, you're successful in the fact that you're living somewhere no other fly can. Like, you're doing something no fly can, but you're only successful in a very, 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 very specific scenario. So it's this like double-edged success. It's very similar to like a lot of extremophiles, where it's like, yeah, you are the only ones that can live at a hydrothermal vent or in a geyser. But if we take you out of there, not so much. Now you're going to compete with all the other bacteria, and you're going to get beat up.
Yeah, I mean, one of the worst things to consider as the most successful are invasive species.
Yeah, that's why they're invasive.
That's why they're so good at it.
Well, it's like weeds. When we talk about weeds, it's like, well, yeah, the weeds are incredibly good at what they do. That's why they're weeds.
Yes.
And there's also an argument to be made that any group of life that is around today is highly successful, because they are a never-ending line of 4.5 billion year old heritage that has made it as far as today, and that is success.
Yeah.
That's an answer. We want specifics. David.
We want names.
All right, specific. Who would I say are the least successful group of animals? I like Brandon's answer of a group that is now dependent on us, especially a group that has lost its diverse. Like, I'm thinking like cattle. Where this is a group, and now on one hand, cattle are extraordinarily successful. They are among the most abundant animals on the planet. On the other hand, evolutionarily, cattle have sacrificed all of their ancestral diversity to become exclusively a tool that is dependent upon humans.
Yep. If you remove us from that picture, what happens to cattle? Versus what happens to pigs, and they go feral and then absolutely wreak havoc.
Although arguably, I guess the same argument could be made about most parasites. Is that if something happens to the host, then that parasite is gone. But at the same time, it's hard to argue that the parasites aren't successful, because parasitism is arguably the best life habit to be on the planet if you want to be diverse.
I'm refraining from this going further into my realm. That is a Common Descent After Dark episode.
Yes.
I think that what we have settled on here, and I think that this is a great question, and I think it really reveals the fact that success in biology is extremely conditional and it's extremely subjective.
Well, like island species come to mind for me of like the kakapo, which is the flightless parrot that is one of I think the heaviest parrot.
Yes, the heaviest parrot, yeah.
Just little rotund parrot, completely flightless, lives in mountains, and so it has to trudge around this mountainous terrain to like find mates and whatnot. And they have really wide territories because the environment can't support dense populations because it's not a rich tropical environment. It's these fairly cold mountainous areas. And it's like, yeah, that's a terrible way to live. Like, you were going to have to, as a parrot, walk like miles to find a mate, which are not walking birds. Parrots are not
among the least walking of birds.
Yeah, so like that is obvious that like that was a bad choice, but if you wanted to be a parrot on that island, that's the way to be a parrot on that island in that situation. Like that's what you need to do to survive in that scenario. So they did what they needed to evolutionarily and were successful. It just doesn't work if anything goes wrong, environmentally.
Yep. If there's not like an ecological redundancy to ensure your success, I mean, what are you doing?
Yeah. It's why we talk about generalists so often.
Yeah. Maybe that's the key, is how resilient a group is
to
change an ecological disturbance. Maybe that's where the success lies.
That's definitely where I tend to lean. Of like, if you resist things trying to get rid of you, it's hard to argue that you're not successful.
Exactly.
Like pests. All pests are huge success stories because we are actively trying to eradicate them, and yet here they are.
To bring it full circle, mosquitoes are extremely successful.
They really are.
Yep.
You've got the ill will of 8 billion people directed at you, and you are still trucking, despite being made of paper.
Yes.
Ava, thank you so much for that question. We really appreciate it. Patrons, remember, if you are at a certain level of patronage, you can submit questions for us to answer here on the podcast. Brandon, thank you for joining us to answer that question and joining us for this episode. Before we say all of the outro stuff, please let our listeners know once again who you are and where they might find you.
I am, again, Brandon Strauss. I am a PhD candidate at Texas A&M. I specialize in forensic entomology. You can find me on Blue Sky and Instagram at Punk Entomology, or just in the Common Descent Podcast Discord. So, I'm hanging out there with the rest of y'all, showing up at Q&As.
So if you have questions about this episode and flies and stuff, Brandon's in the Discord.
Right. And I'm putting the disclaimer, I did not cover everything. I might have misspoke about a few things. Again, some of the stuff was simplified. Don't get too mad at me.
You can also find Brandon at DragonCon. If you come to DragonCon to see me and Will, Brandon is often there on adjacent panels. We tend not to actually be on the same panels, unfortunately.
I mean, you guys do more of the dry, older, fossilized stuff. I'm doing the wet, new stuff.
Our stuff's not ooey gooey.
Yeah. We'll figure out an ooey gooey to do together, I think.
Yeah.
I think this year the Science is Gross panel was at the same time as the Monsterotica panel.
Yes.
If I remember correctly. Yep. And I'm so sorry, but I did make the other choice in that selection.
We turned away like 100, 150 people. So
that's great. I mean, not great for those people, but it's great that you got that.
They're actually considering a ballroom for us next year.
Yeah.
Nice. Excellent. Listeners, come to DragonCon and come listen about science being gross in the ballroom. Make sure to check out the blog post that will be up on our website after this episode. We'll have links and some pictures. So that we will limit the selection of pictures that go into this blog post for convenience and accessibility.
Just all your favorite close-ups of mosquitoes.
We'll make the Brandon page that'll be behind a link. Yes. There's all of Brandon's favorite pictures. Click if you dare.
It's just a we didn't start the fire of insect photos.
Thank you to all of the people who requested this episode topic. This was a whole lot of fun. Thank you to all of our patrons for supporting the podcast. An extra special thanks to our top tier patrons, Sarah May, Jeff Ellington, and Danielle Loves Bugs. Hopefully, this was a satisfying episode for Danielle, who loves bugs. Remember that this episode is coming out somewhere around the end of the year, so our end of the year Q&A either is coming out soon or has already come out. Will and I probably answered questions for 20 or 30 hours. You can go check that out. We had a whole lot of fun. We release episodes every fortnight. Join us next time for some other topic that people wanted to talk about. And one last time, Brandon, thank you so much for coming to join us. This was a ton of fun.
Guys, thank you so much. I've been looking forward to this since Dragon Con when you asked me. I was so excited to do this.
Yes.
It's so good.
Listeners, let us know what other bugs you want to hear about. Brandon, what bugs would you like to come back and talk about?
I mean, I will do beetles. I'll do it.
Fantastic.
Can you hear my voice? I'll do it. We're gonna need some time though.
Yeah, well, we'd have to really sit down and think how we would tackle beetles.
I will take a look at some things, try and come up with a plan attack, because we might have to do it by infra order or something.
Yeah.
We'll do it like fungi, and it'll be a multi-episode.
Yeah, it might have to.
I feel like it's deserving.
Episode 300. We'll bring Brandon back for Beatles.
I'm here for this.
We want Brandon back before that.
So I mean, before that,
yeah, for sure.
But
we can work our way up.
Beatles is our Godzilla, I think. That's a lot to take down.
Beatles is a monster of an episode. Yeah. Listeners, go ahead and submit your topic requests to the request form on the website. And other than that, some kind of pun about flying away. And we'll...
buzz off. Oh,
hey, there we go. We did it.
Hey. Da-da-da-da-da-da.
Thanks for listening to the Common Descent podcast. You can follow us on Facebook, Twitter, YouTube, and check our WordPress blog for pictures and links after each episode. Huge thanks to our patrons whose support helps keep this podcast running and who get access to bonus goodies on Patreon. The song you're hearing is called On the Origin of Species by Protodome, which we found at ocremix.org. Thanks again for listening. We hope you'll join us next time.